Artificial General Intelligence. The local organizing committee welcomes everyone and motivates you to participate in every one of the presentation, interacting, using the space and tools to ask the presenters. Presentation of this conference will be held in 2 rooms identified as auditorium and room. Your presentation will be held in the room indicated in the calendar published on the webpage. Panels and plenary presentation will take place in this auditorium. Now, I am pleased and honored to invite Professor Alexei Samsonovich, who will open formally the 13th edition of BICA 2022. Please, Professor Alexei.
Thank you, Felix. This is quite unexpected because I actually thought that you should open the conference because you are
the general. It's no problem,
chair,
Alexei.
The general chair. If you since you gave it to me already, I say hereby I declare BICA 2022 open. And
okay, no, it's just as simple. Being more or less 8:20 a.m., I declare a start of this 13th edition of BICA AI 2022 conference. Welcome to everyone and enjoy learning and knowing each one of us. We can start to make new relations, new collaborations, showing our work, and you are welcome. And it's a pity that most of you are not here in Guadalajara. Today is a very, very sunny day, and we will have a very, very, very special weather here in Guadalajara. So we start this 13th edition of BICA. Okay, as I said, your presentation will start in the room indicated in the schedule published on the webpage. Okay, we start in 6 minutes. Okay? Well, welcome to everyone.
Thank you.
Okay, so you choose your room, okay? So, sí.
Where is the room? This second room that that are here.
Yeah,
the auditory and the room
is in another room.
Yeah, but how can I find it?
Sí. ¿Dónde está mi teléfono?
Yo soy Ricardo Rubin.
Sí, Ricardo, ya te conocí.
Félix?
Gracias. Muito obrigado. Mi amolia, sí. Sí, você pode falar comigo em português se você quiser. Mas eu compreendo.
Eu quero tentar falar um pouco espanhol.
Porque está. O Dr. Jonathan.
Sí. Hola, Jonathan. Yo soy Ricardo Rubin.
Mucho
gusto, ¿cómo estás?
Bien. ¿Y usted?
Así es. Muy bien.
¿Cómo le fue?
Sí, éxito. Bueno, poquito de dificultad para achar el lugar, pero por sus recomendaciones.
Bueno, tranquilo, sí. Está bastante bien. Déjame ver ahorita porque vamos llegando.
Ya abrimos.
Ajá. Hay que abrir del otro lado.
Hay que abrir
Me gustaría saber dónde era el otro link, pero que no conozco esto.
El otro, acá de este lado. ¿Cómo se abrió acá de este lado?
La primera presentación será a las 8:30. No.
Aventarme al ruedo, doctor Félix, perdón.
Okay, Anton is here.
Yes, hello. Good
Hello.
morning. Good evening.
You can share your screen if you want. We are going to start your presentation.
Okay, so I can share my screen and slides.
Yeah, please.
Okay. So let me go ahead. Okay, so do you see my screen?
Yes, we can see it.
I assume somebody should introduce Anton, correct?
Yeah, yes, it's me. Well, we are going to start this track with the presentation of cognitive architecture for decision making based on brain principle programming, and that will be presented by Anton Kolonin. Please.
Hello to everyone, and thank you for giving me the opportunity to present my work and work of my colleagues to the BICA conference. And I'm going to talk about the cognitive architecture for decision making, supposed to be used for development of decision support systems. And this cognitive architecture is based on the principles of brain activity. We can call them brain principles programming, and this cognitive architecture at the same time is relying on formal mathematical methods such as task-driven approach. We call it TDA, semantic probabilistic inference, we call it SPI, probabilistic formal concepts, we call them PFC, and theory of functional systems, we call it TFS. So let's start with the principles. Let's imagine that we are closing our eyes and someone puts something in our hand, and we try to guess what's that. So we feel the shape. We try to press the object and we feel whether it's hard or soft. We try to move our fingers and feel the surface. Then we also realize the weight. And these different perceptions of different modalities generate some complex picture with, and we can generate different hypotheses and different theories. What's that? And at this point, the principle of generation of complexity is acting. So different theories with different properties are populating our brain and different segments of the cortex of our brain. And then we are trying to map one theory against another, and the properties associated with one theory with properties associated with another theory. Like, for example, we may think that that's a pool ball, but then we think, okay, pool ball should be heavy, and that's not heavy. Then we can think maybe that's an orange, and then the orange should be soft when you push on it, but it's not soft. It's hard. So then there is some interference coming in our brain, and the processes and principles that are leading this interference are called, as we call them, principles of relationship. So we relate different theories and different properties, different objects and different features of this object one to other to see which one corresponds to which. And the other principle is principle of locality distribution. So recognition of the object in space of one particular modality, like shape or weight or color or smell, is done locally in particular segment of the cortex. But at the same time, these different activities are concurrently running in our brain. So we are trying to recognize the object in different modalities at the same time. and then principle of relationship back makes it possible to relate each to other, right? And at the end, the principle of heaviness acts. So due to the principle of heaviness, the theory which is less contradicting to the properties and to our perceptions is winning, and we are coming to decision. What's that? And then the principle of approximation to a sense comes into the play, because let's say we have decided that that's an apple, and that's an apple, but because our eyes were closed, and in our life we have seen green apples most of the time, we approximate the real apple in our hands to some theoretical apple which is green, and then we open our eyes and see that that's a red apple, but that's not a big deal. We still were able to guess that that's an apple. So these principles can be actually expressed and implemented in a few different ways. Historically, in terms of the evolution, these principles are implemented in our brain, and you can find different neurophysiological processes that are corresponding to these 5 principles. For example, the relationship and locality distribution principles can be found in the design of the consciousness proposed by Tononi. The heaviness is something that you can relate with principles of lateral inhibition and winner takes all policies of decision making. But in our work, we are trying to build the system based on the formal mathematical methods, and all of these methods are based on what we call task-driven approach, suggested by Siberian mathematicians. And the task-driven approach, that whenever you want to have a decision-making process system implemented for particular domain, be it some business application or Medicare or some technological process, you need to define the problem in some operational ontology or some operational space, where the operational ontology may be consistent of sensory space of your technological process, or just set of predicates that are described in the business rules. And once you can specify the area of your application in terms of the domain ontology, you can also specify the criteria for goal achievement. Like in order to have the goal achieved or task solved, you can assert that certain properties of certain attributes or relationships of certain properties with certain attributes of one object correspond to the other properties of the other object. So some subgraph in this domain-specific ontology might be corresponding to the state of the technological process or your activity where the goal or task is solved. Okay, and then in terms of the predicates describing this domain-specific ontology, you can apply semantic probabilistic inference, which does logical inference on the predicates built in this operational ontology. And then the inference is done probabilistically, so that's not just traditional prologue style logistic induction or deduction. We count for probabilities. And any model that we can describe in probabilities, we can handle with this probabilistic inference. Moreover, besides the probabilistic inference engine, the other part of the system is probabilistic formal concepts framework, which is an extension of the well-known formal concept analysis design, but we account for probabilities. And in fact, whenever we discover some concept, which is like flying birds, right? So there are birds that are not flying, and there are flying objects that are not birds. But once we identify the concepts of flying and birds, we can also identify some logical relationships between the objects that represent this concept and the properties of these objects in some logical rules, and these rules are exactly the semantically probabilistic rules that can be inferred by semantic probabilistic engine. And finally, whenever we can apply this semantic probabilistic inference applied to task-driven approach and potentially involved in formal concept analysis in some real processes, we can at any point of time, whenever we make some decision, we can generate the action that we have direct toward the world. but we can also generate expectations that we anticipate based on our action towards the world. And then when we get some positive or negative feedback from the world, we can compare our expectations and the actual reaction from the environment. And based on the difference between our expectations and the real feedback from the environment, we can correct our actions. Either we consolidate the positive experience, or we rather destroy some probabilities and decrease some probabilities that were used to cause this action. And that's then the ground for and basics of theory of functional systems by Piotr Anokhin. So let's move towards the architecture that we are suggesting. Let's imagine some real case where we have some manager in a business. Let's say it will be sales manager, which takes care about the sales, and it has the system which logs the history of sales. So every sale or every business event in the enterprise is logged as instance, some object with some processes, and then all instances are going to the probabilistic formal concept subsystem, which also forwards these instances to semantic probabilistic engine, and semantic probabilistic engine inference creates the rules associating different properties. And then if we are finding some reliable and repetitive configurations of the properties, we can learn some formal concepts, performing and supervised learning, so to speak, and then these formal concepts are stored in the database as invariants, and rules that are used to infer presence of these invariants are stored in the probabilistic rules database. And then we implement the principle of approximation to essence, because we are approximating to the essence multiple instances, merging them into some invariant. Then let's say there is a real trouble, and there is an event logged saying that the sales are falling, and the manager has the goal to have profits rather than fall of sales, and there is a request to the system what to do. So here is what is happening now. Again, we have the principle of approximation to the essence. So event of sales falling is causing invariance corresponding to such situation of sales falling, and then there are rules involved that are connecting potential falling of sales with possible outcomes that can follow such situation, and which might be potentially associated either with increasing the profits or decreasing the profits. And then we have all the principles of generation of complexity, relationship, and locality distribution acting all together. So we generate and multiple theories and relate them each to other in given context. At some point, when the most strong theory wins and appears most relevant to current context, due to the principle of heaviness, there is a recommendation directed to the user, and at the same time there is expectation is directed to the module of theory of functional systems. And then when the feedback comes back and the sales actually grow, then we identify the invariant of increased profit, and this increase of the profit is matched by the theory of functional system, which has to compare the expectations about growing sales and the actual event of profit, and the positive experience is consolidated in respect to the rules that were most relevant to in given context due to the principle of heaviness. All in one, here is the cognitive architecture that we are implementing. So in the middle you see the kernel, what we call cognitive kernel, based on semantic probabilistic inference, probabilistic formal concepts, theory of functional systems, and task-driven approach, where probabilistic formal concepts is creating the formal concepts or invariants out of instances stored in the cognitive database and binds them with semantic probabilistic rules. Semantic probabilistic inference is associating and supplying these invariants with rules, proving the validity of these formal concepts or invariants, and also semantic probabilistic inference infers forecasts and directs these forecasts to the user and to the theory of functional systems, which evaluates successfulness of the behavior based on the task-driven approach, and further adjust the rules stored in the rule base, probabilistic rule base. And of course, all these data is being mapped to a specific subject domain ontology in terms of the metadata with types, attributes, and classifiers. So in order to make sure that we are on the right path, we have created different applications, models of the different applications under some unified ontology usable to cover different specific domains. And for example, we have created the application for psychotherapy domain, for customer relationship management domain, and for a project management domain ontology. For example, for psychotherapy, you can see the same way how you can handle, how you can apply these 5 principles of brain activity, but you have just different ontology, right? So instead of shape and weight, we have the state, psychotype of patient, cognitive distortions that patient is suffering from, social situations which is causing such cognitive distortions, emotions that are giving problems to person, and then we are handling not the physical properties, we are handling the patterns of speech found in the words of patient, and then using the same way, the same process as I described in the very beginning, from the single sentence of the patient, we can identify the theory, or which is diagnosis that we need to treat. In this current case, it's anxiety feeling, emotion connected with catastrophizing cognitive distortion because of the person is being fired. And in this example, you can consider simple three-dimensional space. So here is the point of the patient in this three-dimensional semantic space of being fired, catastrophizing, and anxiety. And then the task-driven approach suggests us that the formal task is to move patient from point A to point B. And the point B is the point where which have different properties. So being fired might be still in place because person was fired, so we can't do anything about that, but we can have some therapeutic action towards the patient, so we remove the emotion of anxiety and distortion of catastrophizing. And here is an example of we can actually map these interactions, diagnostic interactions and treatment interactions, to particular flows of speech directed from patient and to neurotherapist, psychotherapist, and from psychotherapist to the patient. And here you can see how particular patterns in the speech are being mapped to particular concepts in the ontology that is underlying the application. And also we have some more detailed description of this process in our paper, and also our paper covers few different applications like for customer relationship management and business and project management. So if you are interested about this work, you are welcome to read our preprint about brain principles programming, which is more fundamental part of it. And here is the preprint of the paper that we have submitted to this conference, where we have more detailed description on our cognitive architecture and business applications. Thank you.
Thank you very much. If someone has some questions.
I have a question.
Yes, Ricardo. Yes.
Hi. My question is, do you have this system available for someone to test, for example, in GitHub or in a public repository where we can take a look on the physical implementation of it, or it's just in a private domain?
Okay, thank you. That's a really good question. Let me see if I have. Well, unfortunately, I don't have email on this slide. So, but I can get you my email in chat, or you can find it out with organizers. So, short answer that we don't have this system in the most of the system is not available in public repositories. So there are some these applications for semantic probabilistic inference, for probabilistic formal concepts, for theory of functional systems, and there are applications, and also for task-driven approach, but all these applications are not open source for the moment. There are some open source developments like experimental results, but this is in hands of one of our colleagues. So if you send me email, I can get you in touch with the person who owns this code. But it has to be sorted out on one-by-one basis because not everything is in open source.
Do you have a plan for making it available in the future or not?
Well, so far I don't aware. So I myself is more on theoretical side. So the people who are working on technical application or implementation of this, they might consider making it open source at some point, but it's better be checked with them. So far I'm not sure about these plans. So mostly technical implementation of the system is in hands of the Evgeny Vityaev and his team. And it better be checked with him. We are relying on his work here.
Okay, thank you.
Thank you, Ricardo. Someone else have a question? Okay, I have a question. And it's very nice to see the formalization of some brain functions. However, all the time I can see that in the formalization we can miss some important variables. Can you say something about the drawbacks has your formalization or not? Or do you think it is completely okay? It's enough?
Okay. I can tell you. So, from my view, the major problem of this of the design that I have been presented today, including these formal systems, is there is a still need to prove that it scales well on the massive data, on the large scale volumes of data, like it has been shown by modern networks based on the transformers and deep neural networks, which scale well with large amounts of data. So far, most of experiments that have been run within the presented approach were run on either small or, I would say, moderate scales of data. And we are interested in applying it to larger scales of data to see that it scales well. So that's the major problem and issue that I see so far.
Okay, another question that I have is, you use ontologies to represent at least a part of a context, isn't it?
Okay.
Yes,
yeah,
so in that way, you ought to create as many ontologies as domain of application you want to use to work on. So is that correct or not? And if that is correct, how you can, how you are planning to normalize or to create, go in the direction of a general ontology or unique representation of a context?
Well, I'm not sure if I get your question, so let me answer and you tell me whether I get it or not. So first of all, in order to do any of these, apply any of these formal methods, you need ontology, or you can call it semantic model, because there are some discussions of if there is what some people mean different things under the semantic model and ontology. We think these are synonyms, so you need some structured representation of some subject domain in terms of the concepts and relationships, more abstract concepts, less abstract concepts, relationship between them, so you need to describe it, okay? And these concepts might be either completely tangible or labelable, like a ship, a road, a port, a device, a person, a human person-to-person relationship, right? A business process, or they may be just corresponding to particular, I don't know, pixels or frequencies, right? So if you want to apply semi-hyperbolistic engine to speech recognition, you can describe every pitch on frequency domain as a predicate, and volume on its particular pitch will be corresponding to value of this predicate. So that's wide definition of ontology. That's on one hand. And then once you define this, you can solve any problem using this approach. On the other hand, in real applications, we anticipate that some complex domains might not have to be described in terms of ontology from top to bottom. Like, for example, part of the system might be called what we call Oracle, which just does some recognition of some properties using, it might be using some neural networks or deep neural networks, and it can output higher level properties or features out of the binary or multimedia objects, and then you operate with that semantic formalism with higher level objects. So that's how it works. I'm not sure if I got answered your question.
Yes, what I see is that we need to have a way to create a context. Yes, once we have a context, we can work in different areas. Yes, but we need to create a context that is suitable for a task, a specific task. That I think you are working or replacing the creation of that context by an ontology. So you need different ontologies, one ontology for each domain. Once you have the ontology, you can work in that domain, isn't it?
Okay, now I think I get your question. Okay, so let's say I will give you, so there are two things. First of all, let's say we want to create two different applications. Like here, you want to create application for psychotherapy, and you want to create application for customer relationship management. And then what we do, and we actually did it, we created two completely different ontologies, which are both based on some unified upper layer ontology, but still these ontologies are different, and they are created at the design phase of the application. So that's one thing, right? So if you have designed ontology for psychotherapy, then application based on that might never be used for customer relationship management. But still, within the psychotherapy activity, as well as within the customer relationship management activity, you're still able to figure out different situations. Like, for example, if the markets are going down, then you need one way to increase the sales. And if the market is going up, then you need another way to increase the sales, right? And then, for example, you might have experience in the system increasing the sales in upcoming or downgoing markets. And in both cases, you might figure out that different measures are needed to handle the sales situation. Okay, and then these two typical markets, like upside market and downside market, they might be considered as different contexts. And then the system should be able, and theoretically it is able, to learn these different contexts, and these contexts are what we call invariants. So in the course of the operations, the system is described that there are goods, there are prices, there are customers, there are vendors. So these are the parts of the ontology that system has to deal with. But it is not, it doesn't have built-in notions of the upside market and downside market. But it is able to learn these proper kinds of the market due to the course of the unsupervised learning, and store them in the database as invariants. And then these invariants can be further reviewed by the human administrator or analyst in the system, and that human might actually label these found invariants like, okay, so this invariant corresponds to in a bull market, and this particular invariant corresponds to bear market. So did I answer this question?
Yes. Obviously, I have more questions, but we have no more time. So thank you very much for your presentation. And now I ask if Shanae Dorknapp is there for the next. I don't know. Sorry for the pronunciation.
It's okay. It's Shani Dorn. It's a difficult name. I understand. Can you hear me?
Okay. You have, as you know, 15 minutes.
Yes, thank you. You can hear me, right?
Yes.
Oh, perfect. Okay. Then I will start and share my screen. Can you see my screen?
Yes.
Perfect. Okay, first of all, thank you for the opportunity and having me here at the BICA 21 conference. I'm Shane Dorenkamp, and I'm going to present our paper, A Controlled Adaptive Network Model of a Virtual Coach Supporting Speaking Up Behavior by Healthcare Professionals to Optimize Patient Safety. Mountful. First of all, I want to talk about the contents. I want to first briefly introduce speaking up behavior in hospitals, therefore also a short background on speaking up behavior in general. Afterwards, we designed a model based on literature that we compiled. And at that point during the description, I will also explain how the model works. And based on this model, we created or executed simulations on situations that may happen in hospital, and specifically in this situation, the delivery department of babies. And then I'm going to discuss our discussion and the conclusions that we found. So first of all, about speaking up in hospitals. As you may know, a medical error during an operation is very detrimental to patient safety, could lead to death as well. And not speaking up about seen errors or reported errors is also very detrimental. So speaking up behavior can function as some sort of safety behavior, which addresses concerns with the benefit of patient safety and optimization of care. However, even though speaking up behavior is a very relevant and important behavior in hospitals or even high-risk organizations themselves, in a recent or in few reports, it has been found that it's very difficult to speak up in practice, as 58% of nurses do not feel safe enough to speak up, indicating a hesitancy to speak up. Therefore, our paper aimed to outline these existing sources of the occurrence of speaking up behavior in risk organizations or high-risk organizations, such as in hospital, using a computational modeling approach, which is capable of representing this behavior in a generative and causal manner. And we also introduce a virtual coach as some type of mechanism to control further prevention of medical errors when, for example, in 42% of the cases, people do not speak up. So I'm going to talk about the overall model structure. So the adaptive causal network modeling, we designed this entire model. It's rather big, but also very interconnected. So I'm going to show you the entire model first before I go in detail for each section. So what I have here is the world state model, which is indicated by the squares. And this is basically what is happening in the world, all the actions that are actually happening in the world. Next, we have an individual model of the nurse, their mental state, where the speaking up is chosen, basically, as well as the doctor. In the situation, you have a nurse and a doctor. In this case, we have a nurse and a doctor, and the doctor can respond to speaking up. A speaking up that is like in the air, or has happened. So we also have that model, as well as the coach we introduced. Yes, so first I'm going to talk about the world state model, which basically is a sequence of actions that are generative based on this case description. We have a very brief description of the case description, which is when a baby is born but is not breathing very well. So there's an intervention called, which then leads to subsequent actions allocated to specific roles of the nurse and the doctor. The moment at W6, where the intervention seems to be insufficient, so the baby is still not breathing, in this situation, we assume the nurse notices a type of error, which then at that point, and I will show you in the nurse model how that works, the nurse can choose to speak up or not speak up, which you can see here. So either the nurse speaks up, they stay silent, and when the nurse does speak up, it warrants a type of reaction from the doctor based on the literature we found. It can be positive or negative. And if they do not speak up, we have this intervention by the coach that we introduced, where the coach can perform some type of intervention or speak up themselves to prevent the error from happening again, therefore, quote unquote, saving the baby and improving patient safety. And important to note is that once the event or the error is found, it also increases the risk of the baby's harm. Next, about the nurse individual model. So what we have here is in the orange box, we have the nurse's individual model. It is a mental model that uses cognitive processes to get to a type of, behavior, which in this case is speaking up behavior. First of all, as you can see in like the previous big mental model or entire model, you saw a connection between the nurse individual model and the world state, which is basically modeling observation. The nurse is seeing what's happening in the world and they respond to that, as well as thinking about what their next step is, which is this sequence that you can see over here. For example, the nurse prepping the patient. The moment, however, where the nurse notices that there's an error, which is at N5, it activates the second part of, or it activates the speaking up system that we created, which is an evaluative decision-making system, which consists of 3 parts. The first part is once the nurse notices the error, it activates 2 evaluation states, which is they evaluate whether they should speak up or whether they should not speak up or stay silent in this case. And as you can see, there's a loop in here. For both evaluation states, there's a loop of stimulus representation. And in that state, the nurse basically asks themselves, what will happen if I speak up? So the stimulus representation states further activate evaluation states, which means that either one choice or either evaluation state will be chosen to then choose speaking up or stay silent. And important to note, in the literature, we found that an important mediator of speaking up is psychological safety, which entails feeling safe enough to speak up, which can be influenced by individual factors, which we have noted here are skills, experience, and training, as well as fear for repercussion. If there's a lot of fear, there's a lower chance or there's a lower psychological safety. Also important to note, all the orange arrows are negative directions, are negative relationships. So fear suppresses psychological safety. As well, psychological safety can also be influenced by higher or by organizational factors, such as organizational psychological safety and, for example, the team and how much they trust themselves, as you can see here, team psychological safety and the organization, which also feeds into their own perspective of safety. So let's say if there's a high psychological safety, then the nurse will choose psychological safety. At this point, it activates the preparation state evaluation system, where the nurse prepares to actually do the action of speaking up, which can also at that point be influenced by, let's say, stress. And we have here a control state, which lightly suppresses the action of speaking up or silence, because it should mimic or model hesitancy, as well as harm, or the perceived patient harm. How harmed is the baby should also influence whether they should speak up or not. So you have either speak up or not speak up based on this system. Yes. So that is shown here. They can show either speaking up or not speak up. The next is the Doctrine visual model, and we attempted to model this because the response to speaking up can also affect future behavior of speaking up, or the fear of speaking up, and I will show you that in a second. Even though there's less literature on this, it's still important to have a foundation of how can be responded to this. So at this point, the doctor sees or observes that the nurse has spoken up. At that point, this is the same system of the observation system as well as what action am I going to take next. So once the doctor notices that the nurse has spoken up, it activates some type of receptivity system. How receptive am I towards reacting positively towards speaking up? So that's this D12 over here, which can be influenced by the amount of stress the doctor has and the fatigue, as we have found. If there's a high amount of stress and high amount of fatigue, it will repress or decrease the chances of the nurse being able to, or the doctor receiving the speaking up behavior positively. And then it actually activates a similar system as I described before. So it's the same evaluative decision system with a stimulus response loop, an evaluation loop, and preparation loop. So either a positive response will turn out of this, or a negative response. And if the doctor has responded, it's either positive or negative. Yeah, basically that. And this is the introduced coach that we have, which is an almost identical copy of the nurse, but has the values of the nurse when they always speak up or always choose to speak up. There's always, for example, a high psychological safety in this coach. The only difference is what is important is that it should not activate before the nurse has spoken up. So that when the nurse does speak up, this coach can, for example, get some information from the context. It should be repressed over here. This is our context or control state. This threshold of the state is so high that if there is if the nurse speaks up, it should not activate this state to then further allow the coach to intervene in the situation, which can be shown over here. So as you can see, there's, for example, silence has a positive response or positive connection with the choice to speak up of the coach, as we introduced. So high, for example, the nurse does not speak up after a long time after the error has been noticed, also by the coach, then it should activate this state, this control state, enough to further activate the intervention of the coach. And in the same manner, when the nurse does speak up, it should repress this state of the coach. So there's not enough activation to do the intervention. Okay, this is the entire model. So what we have done, we took a case analysis or a case study by provided by a neonatologist, where after the delivery, a neonat's not transitioning well. As you can read here, the baby is blue, and even after stimulating, it's still not responding. So they perform a ventilation or a mechanical ventilation. However, this ventilation is not boning well on the baby. Therefore, even though, because the baby is not stabilized by the use of the intervention, there is still no chest movement. And at that point, as you can read here, the nurse notices what the error is. And at that point, they can give a suggestion to the doctor, but then they first have to decide whether they will speak up or not speak up. So we did some simulation experiments. We have a baseline simulation here, which shows that there is no activation of WS6, which is the is an insufficiency of the intervention, because intervention was successful. Therefore, there was no need to activate for the nurse to speak up or even the coach to speak up. As you can see, there's no activation of either of those states. Next simulation we did was speaking up with the doctor's positive response. So first, I'll show you the graph that we had with some illustration of the loops that I talked about. This basically shows how one evaluation state was chosen. So in this case, the N10, the evaluation of speaking up was chosen, and the silence was further repressed because it could not be chosen. Oh. And these are the preparation states that activate after the choice was made, basically, which then triggers activation of speaking up by the nurse. The second graph shows you also the nurse speaking up, as well as, I did not talk about this before, but there's also some type of stress always assumed when you have to make a decision, especially a decision such as this with such a risk. And as you can see, what's happening, that the stress lowers after the nurse speaks up. And here is the prevention of medical error, which is an action taken when the nurse speaks up about the error, as well as the increase of patient safety at this point. And here you see the doctor's response after activation of the speaking up behavior by the nurse. And here you see the high receptivity to the speaking up behavior that we modeled before. So there's a lower amount of stress and lower amount of fatigue, basically, which triggers then the positive response by the doctor. And an important factor was, as stated, is fear for repercussion, so negative consequences on, for example, speaking up. Fear lowers, as you can see here, it's this graph, lowers the moment the doctor has a positive response to their suggestion. So we can, even though this is a singular event, it's an assumption that next time there will probably be less fear to speak up in the future, which leads to higher psychological safety. Okay. And here we had these states for psychological safety, which are rather high or which allow speaking up to happen. The next simulation we did was speaking up with a negative response, as you can see
we are
here.
running out of the time.
Oh, really? Okay.
Yeah.
Should I just quit or go to the discussion? So there's a negative response, as you can see, with low receptivity, high stress, etc., as well as decision stress and increased fear. And also lower amounts of psychological safety at the end. And here is silence, quite simple to see. Lots of fear, organizational, it's all very low, which allows the nurse to not speak up. And this shows the intervention of the coach, which should lower fear in the future, even though the nurse did not speak up because of the low amounts of psychological safety. But patient safety increases, which is an important aspect of this paper. The conclusion is that this paper demonstrates how speaking up behavior can occur in healthcare professionals, but we have some limitations as the study was based on literature mostly. So we want to validate with data, and we could like use more factors that influence psychological safety, such as you can read here, leadership hierarchy, etc. And now we only measure a singular event. But it does provide a good baseline for future models of speaking up behavior, as important as it is in hospital settings. Thank you for your listening. Do you have any questions?
Yes, someone? Questions?
I have a question.
Yes, sorry.
Hi, it's indeed a simple question. I noticed that in your model you have squares and you have circles. What is the difference between them?
So the squares, I have a lot of things here. The squares basically indicate the world state model, which show these are the actions that are actually happening in the world, as you can see. They're only based on, so for example, you speak up and that is actually happening in the world. The round states that I have are mental states. So that's only happening within the nurse, in the context, or within the doctor.
So it's a kind of a premise that is happening. You don't have a way of controlling them.
You don't have a way of?
It's just a premise that you have on them. You cannot observe it happening because it's inside the mind of the person. It's
indeed in the mind of the person. That's why these assumptions were made based on the literature that we found. And I think, as you say, yes, it's a premise. So therefore, we could be able to validate the validation or the accuracy of these states with further, let's say, questionnaires to better predict whether speaking up can happen, for example.
But both of them are events. Both the squares and the circles are events. The difference is that the squares are observable and the circles are inside the mind of someone.
Yes, basically.
Thank you.
Okay, someone else? Questions? Okay, thank you for your presentation. Was great. It's very interesting. Okay. Ya le pones ya está activado el micrófono.
Good morning. Good morning. Good morning. My name is Tania. I'll be the chairman during this presentation block. We shall start with Dana's presentation. Are you ready, Dana? Dana, are you ready?
Hello. Yes, I'm ready.
And you have 15 minutes to present your work, followed by 5 minutes of questions from the audience. We remind everyone on the audience to please mute your microphone.
Okay.
Dana, please go ahead.
Okay, can you see my screen? Can you see my screen?
Yes.
Yeah.
Okay, thank you. So I'm delighted to be here and be able to present our work that is called Formal Representation of Natural Language Elements in Multi-Agent System based on Self-Organization of Distributed Neurocognitive Architectures. The paper proposes an approach to the formal representation of natural language elements based on multi-agent recursive architectures for solving problems of speech recognition, understanding, and synthesis. This approach, based on intelligent software agents with developed cognitive architecture, makes it possible to represent linguistic information at all language levels, from specific morphological to abstract semantic. A big amount of language processing systems used subsequent architectures that were easy to assemble but had limited functionality. About 40 years ago, it was first discovered that distributed system can be a possible alternative for a natural language processing system, since it's possible to develop interaction between autonomous, specialized, and distributed modules. In order to model an artificial intelligence system able to represent elements of natural language while solving complex problems such as speech recognition, understanding, and synthesis, a multi-agent cognitive approach can be used. This approach is based on the computational abstraction of multi-agent neurocognitive systems that model the architectural correspondences of neural connections in human brain, which makes it possible to develop a model that can learn independently, recognize and measure data flows using the acquired knowledge, context, and experience. In our system, we have combined two methods of representing linguistic information in a multi-agent system: lexical, structural, and cognitive linguistic approaches. In the first case, agents are associated with morphosyntactic categories of words and display appropriate behavior. In particular, they exchange messages and search for agents with whom they can enter into contracts, thereby building relationships of a more complex level until the entire multi-agent model of utterance is represented. In this case, speech recognition, understanding, and synthesis is carried out via the grammatical rules of the language. This idea is close to the dependency grammar theory, since it involves application of the principles of following and dependence of immediate constituents of utterance, which ultimately leads to the modeling of the structural representation of the statement. The second approach assumes that agents of different types are presented in the system, which corresponds to the different language levels: morphological, syntactic, semantic, and lexical. In the system, the lexical, within which the morphological and syntactic levels are implemented, and semantic levels are implicitly represented, which is due to the assumption that we need two types of agents to represent the meaning in the system, that is, agents words and agents objects or concepts. Word agents store phonetic information, paradigmatic and syntagmatic relations. Concept agents contain in their knowledge bases a description of an object corresponding to a given word. A contractual relationship is established between two agents and store different information about the same language unit. The activation of one of them entails the activation of the other. In our opinion, such division of agents corresponds to the Broca's and Wernicke's areas in brain. Broca's area is responsible for the production and memorization of speech, and Wernicke's area is responsible for the activation of images and concepts. At the lexical level, agents of different parts of speech are implemented, main and functional words. When a word appears in the system, it initiates the creation of its corresponding semantic agent. In addition, depending on the part of speech, that is, agent type, begins to search for words that can conclude a contract with it. A request for a contract is a question corresponding to the part of speech of the word. For example, agents words that are nouns ask question. Who will buy information that answers the question, who or what? In the agent knowledge base, this is represented as follows. Only agents related to noun by syntactic relations can respond to such requests, that is, adjectives and verbs. Thus, the conclusion of contracts causes the creation of structures of higher level, namely a noun phrase, a verb phrase, etc. In accordance with the dependency grammar, relations are established between words that are verbs attract nouns, pronouns and adverbs to themselves. Nouns attract adjectives. Thus, agents in the system are considered as units of knowledge, and the compositional meaning of the sentence is derived via interaction between agents. They try to find those agents with whom they can conclude an interaction contract. Obviously, contracts are not made randomly. They are based on the principles of dependency grammar and energy search. Agents interact by sending direct and general messages. Thus, agents of verb type send messages to nouns and pronouns to objectify their valency. The process of speech synthesis begins with training. The word document is entered into the system via the editor, that is, a user interface to the system. As the input was made from the keyboard, a lexical agent of the noun type is created. This type of agent initiates the creation of the corresponding semantic agent of the object or concept type. Contractual relations are established between them, which guarantee the recognition of themselves and the contractor in the future. In our conception, we doubt that objects are not remembered separately from the context. That is, an object or a new word is not reflected in memory without the corresponding action verb. For this purpose, in the knowledge base of agent of the object type, there is a rule which can be described as follows. If an agent of the object type appears in the system, it initiates the creation of the corresponding action. For this, it's necessary to send a request to the user. What does the object do? In response to this request, we enter the verb appeared. For example, it can be any other verb that we need from the keyboard, after which an action type agent with the corresponding name appears in the system, which in turn initiates the creation of an identical lexical agent. After its appearance, the action sends a request to all objects, who will buy information that answers the question, what does it do? An object agent that has the status, I'm waiting for my action, reacts to this message and a contract is concluded between them. Then they send their data to the next, more complex level to create an agent responsible for this event. The article presents the implementation of the combined approach of representing natural language elements. Its indisputable advantage is the combination of two approaches that allow simultaneously creating agents for each individual word, taking into account its part of speech affiliation, linking them with contractual relations based on the dependency grammar. In addition, the relations of language levels from morphological to semantic are realized. This combination of approaches allows the system to be dynamic, which is explained by the presence of pre-created agents in the system, as well as the possibility of creating new agents of different types during the learning process. I think that's all. Thank you for your attention, and I'm ready to answer your questions.
Thank you, Dana. Now we will proceed with the question from the audience. If anyone has any question, please raise your hand.
I have a question.
In this system that you are creating, is it possible to realize the perception of time passing? I mean, a situation where something that is moving and linguistically detects this passage of time and in some sense registering it.
Yeah, thank you for your question. Yes, it's indeed possible because this system consists of different constituents, and one of them is camera. And camera is used by the system like we use our eyes. And when we see something, or when the system can capture something using its camera, these events are created in the system using these agents, and of course time is captured as well according to the different perception tracks that are about vision in this case. And we have time agents as well, different kinds of agents, not only linguistical one, but time, location, and others.
Okay, thank you.
Thank you.
Thank you. I see we have no question. No. Okay, so we'll proceed with the next presentation. Andre, are you ready to share your screen?
Hi, can you see my screen?
Yes. You have 15 minutes to present your work, followed by 5 minutes of question.
We can.
Recording in progress.
Petr Kuderov is there. No.
El siguiente módulo.
Well, we are going to wait some minutes.
But what was wrong? I thought the talk was going on okay. Why was it interrupted?
Was interrupted because she ought to be in the room, not here in the auditory.
Was it really a problem? Okay.
She realized that, so she changed the room.
From my point of view, it doesn't matter.
Yeah. So Petr Kuderov. Petr Kuderov is there. No. No, he's not there.
Yeah, but he was expected to be here by 9:40.
Yeah, we are going to wait.
We need to wait for him.
Yeah.
Could appear. Who is missing is Andrei Netyubin or Sergei Mizurin.
Exactly. Sergey, no?
No, tampoco está.
Ok. ¿Y el otro?
André. Tampoco.
One of the main problems that I have.
Petr Kuderov, are you here?
Yeah, I hear you. Hello.
Hi. Are you ready? You share your screen?
Yep. Wait a second.
Yes, please. You have 50 minutes to present your work, followed by 5 minutes of questions from the audience. We're reminding everyone on the audience to please mute your microphone.
Okay, thank you.
Please go ahead.
Oh, sorry. Hello, I'm Petr Kuderov, and I'm here to present you our work about spatial temporal processing. An important difference between natural intelligence agents and artificial intelligence systems is that it's natural for the former to work with streaming data. The data that have not only spatial but also temporal structure, temporal causality. Such data is called spatial temporal data information. And our brains are pretty good at processing spatial temporal data. We can extract and work with abstractions like such as places or objects or melodies and so on. And it's natural for us to work with hierarchy of these abstractions. And it is advantageous for us because for like for solving problems or for learning a model of the environment around us, because with hierarchy, we can greatly reduce the space we're operating in. So the natural intelligent agents are good at it, but on the other hand, AI systems nowadays are struggling with competing with us and these abilities. So the way biological brains perform spatial temporal processing may inspire us to develop better AI algorithms. So the main goal of of our work is to study the ways of organizing spatial temporal processing using one biologically plausible model of human neocortex called hierarchical temporal memory. I will discuss about it a bit later. For now, this hierarchical temporal memory model also is supplied with the framework of different algorithms, and one of these algorithm is a spatial temporal processing algorithm called union temporal pooler. And in our work, we studied this union temporal pooler algorithm. We also try to dissect it to different parts and study these parts in order to get insight of which parts bring which effects on its performance. And so finally, we propose an alternative algorithm, which we call sandwich temporal pooler. And we compare it with union temporal pooler and showed that it has better, more stable, it outputs more stable sequence representation. So before I proceed to discussing algorithms, let's start with the question what we desire from spatial temporal processing algorithm. And the first property we desire is to preserve as much information as possible. However, we do not know in advance which information is useful for us, so we can use a proxy constraint. For example, we can constrain it to preserve similarity between any pair of sequences. We still can distinguish these sequences from each other after processing. And the second property is to improve the stability of representations. We want to time compress the input sequences in order to faster react to what we see. So these two properties are kind of counterbalancing each other. So we have to find a balance between them. How we can measure these properties? The similarity, the ability to preserve similarity, we can measure with an absolute error between two similarity matrices. The first similarity matrix is calculated with input sequences. We calculate similarity between each pair of these sequences, and we do the same with the output sequences, getting two similarity matrices, and then just taking mean absolute error between them. And the second property, the stability, we can measure with we measured with probability mass function coverage. It's kind of similar metric to entropy. with this metric, how we calculate it? We at each step, while we processing a sequence, at each step we accumulate statistics of activations on the output, and we accumulate histogram of activations. After normalizing it, we can get a probability mass function, and then given the probability mass function and current output, we can match them and look at which part of this PMF was covered by the output. And the ratio is the answer. So we can get it each step and then taking the mean, taking the average during the whole processing of the sequence. Okay, now let's get to the algorithms. Both algorithms are implemented using the hierarchical temporal memory framework. It is the biologically plausible model of human brain, of human neocortex. It is based on a model of pyramidal neuron, which has different types of connections. It has, besides feed-forward connections, which are common for artificial neurons, it also has modulatory connections present here. These connections only augment how the feed-forward information would be processed. So in this model, we operate with discretized spikes. So technically, we operate with binary vectors, with sparse binary vectors. And in HTM framework, HTM framework contains several algorithms. In our work, we use 3 of them. The first one is spatial pooler, which is unsupervised algorithm used for clustering. Basically, it is just a perceptron with binary connections and top K activation function. And it is learned with Hebbian rule. The second one is temporal memory, which can learn sequences, and after learning, it can predict the next element of sequence. And the third one is the union temporal pooler, which is studied in our work. It is also unsupervised algorithm for spatial temporal processing, and it is combined with 2 parts. The first part is the common spatial pooler, and with added additional learning rules. And the second one is union pooler, which is kind of one-to-one accumulating layer, which kind of accumulate the traces of activations of spatial pooler. And it also has top K activation function to preserve sparsity on the output of UTP. And so the 3 learning rules that are used in union temporal pooler are the standard spatial pooler learning, union-asder learning, and the history learning. Standard spatial pooler learning is a Hebbian rule. Union-asder learning we can reinforce those neurons of spatial pooler that correspond to the current output of a union temporal pooler. And we reinforce it to the current input. And the history learning rule is we reinforce current activated neurons of spatial pooler to the moving history of inputs. In our work, we conducted an ablation study of these learning rules and found out that the standard spatial pooler learning is the most important to maintain similarity on the output. But it also decreases representation stability because spatial query tries to increase the entropy on its output to make all neurons to participate in how it works. And two other learning rules are used to stabilize the output, the output sequence, and has almost no effect on the similarity, on the preserving similarity. Okay, and finally, we getting this information about these learning rules of union temporal polar, we propose another spatial temporal processing algorithm, which we call sandwich temporal polar. It's called sandwich because we kind of wrap union pooling with two spatial poolers. In union temporal polar, it's just one spatial pooler on the input, and we add another spatial pooler to the output. It allowed us to use longer time horizons for union pooler to accumulate. So we accumulate with less decay, so it can accumulate longer information on longer parts of input sequences. And the second spatial pooler, which is added to the output of this pooling layer, is used to propagate all of this accumulated information to the output. Because in union temporal pooler, activation function is just use top k of the active traces. And so it kind of throws out all other active parts and throws out maybe necessary information which is accumulated in it. So we decided to pass all of this information to the output. And union and spatial pooler is good at preserving similarity. That's why we used it. And the results show that the results was a bit surprising because we didn't find any differences between them in terms of preserving similarity. They are kind of on par in that. But we found that the sandwich temporal pooler gives us a bit better stability, and it is because this information that is lost in the union temporal pooler when it is activates its output, kind of used for maybe used to make different sequences that was that temporal pooler saw before from each other, because different details of which are contained in these sequences are kind of lost in union temporal pooler, but they are propagated in sandwich temporal pooler, so it can better distinguish them from each other and make more stable representations of them, because they don't interfere with each other. So, but we also found interesting properties of these temporal poolers, in that sandwich temporal pooler kind of discards low similarity at all. So if you look at here, input sequences, this is similarity. These are similarity matrices from input similarity matrix, then it's an output similarity matrix for the sandwich temporal pooler, and this is their difference. So if you see here, you see that there are a lot of pairs of sequences with low similarity, and sandwich temporal pooler kind of cuts it out entirely, while union temporal pooler also has this effect, but preserve a bit more of these small intersections between them. And however, we didn't test it in real environments to understand whether this property is useful or not. In our work we thought that we don't need any like noisy intersections between different sequences, so we can cut it out. But it can be useful in a real world scenario, and this is what we think to do in our future works. We want to try out these algorithms in 3D environments, reinforcement learning environments.
Presentation.
Yeah, I'm almost done. To get the real measure of which properties of spatial temporal processing is enough and which is not enough. Thank you. And I also want to say thank you to my colleagues Ivan and Alexander. Thank you, guys, and thank you for listening to me.
Thank you, Petr. Now we will proceed with the question from the audience. If anyone has any question, please raise your hand.
I have a question. Hi, Peter. It's a very interesting work you presented here, but I have a question that is a problem for the original hierarchical temporal memory from Jeff Hawkins. How do you work with different time scales? I mean, you can have sequences that are happening in milliseconds or microseconds, and things that could be happening in hours or days. Do you have a way of dealing with this different kind of time scaling in this time integration that you're doing in your algorithm?
Well, in our work, we work with initially discretized sequences, so we don't need to discretize it and to deal with scaling problem. So we just used the synthetically generated sequences. But if you regarding your question, building a hierarchy of these spatial temporal processors, we can kind of scale out the time, so and work on different time scales. I think that's what we are planning to do in our model of cognitive agent in future. We're kind of building a spatial temporal hierarchy, and so it kind of it enables us to work in different scales of space and time. That's how I think we will do it.
Okay, thank you.
Yeah, Ivan, thank you. Dynamic change of pooling decay can also may solve this problem. Yes. It's my colleague answering your questions too. That's decaying parameter, which kind of which defines how you accumulate your information over time in the union layer. So with bigger decay, you kind of forget faster, and with lower decay, with lower decay, you forget lower. So you can kind of define the scale you want to work in. I hope I answered your question. Thank you, Mom.
Okay, something? Thank you.
Thank you very much.
We have no questions? Okay. Okay, Ivan Rodkin say dynamic change of pooling. Dynamic, Ivan Rodkin say dynamic change of pooling decay may solve this problem.
Yeah, I have already read it out, and it is my colleague, so it kind of he was answering my question too.
Okay. Thank you. We will now proceed with the next presentation. Good day, everyone. My name is Diana Gomez. I will be the chairman during this presentation block. We shall start with Luis Felipe Rodriguez presentation. Felipe Rodriguez, are you ready to share your screen? Sorry, is Enrique Osuna. Enrique, are you ready to share your screen?
Yes, I can show it.
Okay.
Give me a second.
Yes. You have 15 minutes to present your work, followed by 5 minutes to question from the audience.
Okay.
Enrique, you can begin, please.
Okay, hello everyone. I'm Enrique Osuna, and I will present to you this work entitled Towards the Construction of Computational Model of Emotion from the Perspective of a Software System. Okay, computational models of emotion are software systems that attempt to simulate the process of human emotion. And the development process of this kind of models is dual in the sense that it requires a theoretical foundation underlying the model, and there is a computational basis that support the implementation of this model. So these two elements are combined to create a functional computational model of emotion. And after that, commonly is integrated into a cognitive agent architecture, or simply an agent. Some efforts to systematize the design and construction of CMEs has been reported in literature. For example, Hudlika identified a series of computational tasks necessary to implement affective processes and analyzes how these basic tasks can provide a basis for the development of more systematic guidance for the development of this kind of models. Another effort was made by Brockens, who proposed a formal notation for the declarative semantics of the appraisal structure to facilitate the integration of appraisal theories, as well as the design and validation of models of emotion based on appraisal theory. So despite these efforts, there is a lack of theoretical and computational principles to guide this design and computational implementation of the models of emotion. So similarly to these two researchers, different models has been reported has been focused on implementing a variety of affective processes. As we can see here in the table, some of the models, most of the models implement an appraisal mechanisms, an emotional state, a mood state, a personality state, but not all implement a goal representation, for example, or emotional memory. So the variety of affective processes that a model of emotion include is different for one to another. In this sense, despite the variety of processes implemented in models of emotion, there is a series of challenges that need to be addressed in order to achieve CME that model various phases, mechanisms, and components of the human emotion process. So we argued that some of these challenges are very close or are associated with a computational nature of CMEs, and the need to design CMEs by adhering to convenient software practice and utilizing software artifacts. In this context, instead of following a well-known strategies of software engineering, such as those related with iterative and incremental development, contemporary CMEs are commonly designed in an ad hoc manner. And this can be an issue because it can lead to CMEs that model very specific aspects of human emotion and whose evolution could involve a complete redesign. So in this work, we analyzes the model of emotion from a software system perspective, as you can see in the title, and we introduce 4 challenges associated with their development process in order to allow this kind of model to model the emotion in a gradually manner. The first challenge is software quality attribute in the context of CMEs. The number 2 is interoperability between CMEs and cognitive components. The third challenge is formal procedures for the design of models of emotion. And the number 4 is reference schemes to validate CMEs. Regarding the third challenge, the software quality in the context of CMEs is, from a theoretical perspective, appears to be a very complex and ambiguous situation, because the difficulty in defining complete and unambiguous specification in terms of the components that need to be included, the operation cycle to be executed, the terminology used to refer the different emotions, states, and other elements related to its operation. However, the software quality of this kind of model from a computational perspective seems to be more understandable and easier to approach. And even more if we consider a major area such as software engineering that can provide with different stages, such as planning, analysis, development, implementation, programming, design, testing, and validation of software system. So here we can see two architectural representation of 2 different models of emotion that has been reported in literature, and we can see how this architectural representation focused mainly in explain the different interaction among the affective processes, and not too much in explain implementation details of the model from a software engineering perspective. And this can be an issue. For example, this can lead to a little or not possibility of reusing the models or their components because this lack of implementation details. And number 2, difficulties in adapting the CMEs for its use in application or environments others than those for which they were specially designed. Another problem or difficult can be to extend their size by adding new functionalities through models or removing existing functionalities. Other issues can be CMEs that can efficiently exchange information with other software entities. And the issue number 5 is to design and implement modular CMEs. Is difficult, where each component encapsulates its functionality independently. In order to research in other research areas such as mathematics or bioinformatics, computational chemistry, and physics, the inclusion of software quality attributes in the scientific application vein development has been made possible by the adoption of well-established software engineering methods and quality models. So we argue that the solution to these kind of problems can be proposed in these other research areas, and we can tailor or adjust them so together with good software engineering practice they can be used in the context of the models of emotion. The challenge number 2, interoperability between CMEs and cognitive components. The purpose for building a model of emotion is to be incorporated into a larger system or a cognitive agent architecture to improve the relevance of the behavior exhibited by an agent or a specific agent. And this leads to an extensive influence of cognitive entities on the entire development process of CMS. Despite this need for interoperability between cognitive and affective components, and that CMEs are essentially software systems, the lack of adherence to software engineering practice during the development of this kind of model leads to difficulties in achieving such an interoperability. Here we have another example of a model of emotion that suggests the importance of integrate the processing of the model of emotion itself with other external entities of an agent architecture. For example, here in the left side of the picture, we can see that it's very important to consider elements such as psychal context, past experience, social context, personality, culture, and other information from the agent architecture, and need to enter in the model of emotion and be processed, included in the processing of an emotional stimuli. And on the other hand, also this model needs to communicate with agent architecture to provide an effective meaning of a stimuli in terms of action selection or planning, expression, learning, and other components. The following are software engineering practice that can contribute to the achievement of interoperability between CMEs and cognitive architecture that were developed independently. The first element is to use a software design patterns in the context of models of emotion. Software design patterns are a common and reusable solution for software system, and especially this pattern named adapter pattern can provide with defining interfaces to communicate models of emotion with external entities such as cognitive components. The number 2 is the use of comprehensive notation for describing models of emotion architectures, and this description can be in terms of properties, the structure, the components that implement, the collaboration between the components, implementation, and examples of code. And these elements is usually described when a software system is designed in the context of software engineering. So it could be useful as well in the context of model of emotion. The number 3 is communication protocols between CMEs and cognitive components. Of course, if two elements are going to exchange information, need to be a protocol to control this communication. So the use of common data exchange formats such as XML and domain-specific semantics can help to provide protocols for the communication. The challenge number 3 is formal procedures for the design of CMEs. The development process seems to follow the next stages that we can see in the picture. First, when we create or construct a model of emotion, there is a selection of theoretical foundation or emotional theory, and also there is an interpretation of this theory of emotion, and then there is a stage when we design the model, and that implies to specify the operation cycle. After that, there is a computational codification when we use algorithms or specific programming language to implement a computational version of the theoretical foundations. After that is commonly to integrate the model of emotion in a larger system, such as agent architectures. And finally, there is a validation stage. Of course, not all the models consider all these stages, but mostly does. The described procedure seems to result in a CME that emulate particular aspects of emotion and are useful in a specific application domain. The development process of CMEs can be improved with what's best practice, guidelines, methodologies, standards, and other suitable software engineering and tools. So to address this situation, 4 specific tasks are defined that can complement the process described above in order to improve the model of emotion design process. The first one is the elaboration of architectural design of the model, which allows to identify the main components that will be implemented. The number 2 is the definition of a coherent and consistent operation cycle of the model that refers to the order of execution of different affective components that are implemented in the model. The number 3 is take a modular approach to separate the different affective process during the model of emotion. The number 4 is a definition of proper data structures to represent affective information. To design these data structures and his algorithms are required to manipulate is an essential requirement to achieve models with software quality attributes.
Enrique, you have to.
Okay, I will just pass to the conclusions because of the time. We also propose a framework that try to achieve or consider these proposed challenges. In this, well, there is two layers in this framework that we propose, and I will just go to the conclusions. Although the challenges discussed in these papers focus on computational aspects, the development of CMEs can be improved considering software engineering practice. So we hope that this work contributes to the state of the art by first broadening the picture of the challenges that researchers need to consider in order to build computational plausible models of emotion. 2, by highlighting the importance of adopting software engineering practice, especially during the design and implementation of models of emotion. And number 3, contributing to the generation of new lines of research aiming to systematizing the development process of CMEs. If you want a more detailed description, maybe you can consult the paper where we detail where we explain in more detail all these challenges and the framework that we propose itself. Thank you for the presentation.
Okay, thank you, Enrique. Now we will proceed with a question from the audience. Please raise your hand. Question? Question? Okay.
Hi. How do you propose to validate the quality of software?
How I propose to validate the quality in the models or quality attributes? We in this work we refer quality from software quality perspective. It is a term from software engineering such as reusability, flexibility, scalability. These terms are not functional requirements of the system, and give to the model specific properties to expand or to evolve the model. It is difficult to validate, but we believe that software engineering have already some metrics and models to validate this kind of software quality attributes. We are considering analyze them to select a proper metric and model validation for models of emotion.
Okay. Then you propose to use the same metrics to validate software architect in cognition, like
not the same metrics, but we can analyze them and see how we can adapt them in the context of model of emotion. And of course, it's a work that is a bridge that need to be addressed in the investigation. We need to see which metrics can apply, which not, and tailor it in the context of model of emotion.
Okay, thank you.
Thank you.
Is there other question? Okay, thank you, Enrique, for your participation. It was great.
Thank you for your attention.
Okay, we will continue with the next presentation. Claudia Shitty, are you ready?
Hello, yes, we're ready.
Okay.
Thank you for the floor. I'll be sharing the screen.
You have 50 minutes to present your work, followed by 5 minutes of the question for the audience. Claudia, you can begin, please.
Yeah, so we have decided to focus on creating an adaptive network model which simulates the role of the gut microbiome on the circadian cycle, which is the 24-hour body clock, on mood and on insomnia, which is the sleep disorder where you struggle to fall asleep, through the gut-brain axis. Next slide, please. So the microbiome is the population of microorganisms that live on your body. And here we focus specifically on those in the gastrointestinal tract. So the composition of this microbiome affects different biological processes in your gut. So these can then travel along the microbiome gut-brain axis using neurotransmitters, hormones, or inflammatory cytokines. And these then affect the biochemistry of your brain, in turn affecting mood, circadian rhythm, and insomnia. Next slide, please. There's three main pathways which are part of this microbiome gut-brain axis. So there's the neuroendocrine pathway, the immunoregulatory pathway, and the vagus nerve pathway. But we decided to focus on the neuroendocrine and immunoregulatory pathways because we wanted to focus on the endocrine and immune systems and how these work to regulate different hormones, which are important for a regulated sleep cycle. So we've got the neuroendocrine pathway on the left, and this is where the endocrine cells in the gut are stimulated by these microorganisms of that gut microbiome. Depending on what these microorganisms are, it depends on what these what molecules these bacteria are secreting, and dependent on that, different neurotransmitters are released that then travel along the bloodstream along the HPA axis, which is the hypothalamic pituitary adrenal axis. This pathway coordinates the body's stress response, and it does this through coordinating cortisol regulation, cortisol being the body's main stress hormone. So tryptophan metabolism is also regulated through this pathway. Tryptophan is a precursor of the hormones serotonin and melatonin, which are the two main sleep regulating hormones. We then have the immunoregulatory pathway, which is the pathway to the right, where immune cells in the gut detect pathogenic microorganisms, which would cause these cells to secrete pro-inflammatory cytokines. And these cytokines travel along the bloodstream and can cause inflammation all over the body. Sometimes these pathogenic bacteria can produce neurotoxic metabolites. This travels along the blood to the brain and can cause lots of damage there to different molecular processes, which can affect mood, circadian rhythm, and can increase the chances of insomnia or worsen insomnia that the person would already have. This can cause inflammation in the gut, so you can get a leaky and inflamed gut, meaning that these toxins released by the bacteria pass from the gut and then into the blood. Next slide, please. So if you want a healthy microbiome to reduce your chances of insomnia or improve this condition, you can try to reduce your stress levels, have a healthy diet, maybe take some probiotics, because lower stress means lower cortisol levels. And when cortisol is too high, this can dysregulate your circadian rhythm. This also regulates the clock genes. Clock genes encode the proteins that regulate that circadian rhythm. So we chose to focus on two probiotics, Bifidobacterium and Lactobacillus, because these are both found naturally in a high concentration in your gut microbiome. They have very beneficial effects in upregulating serotonin and melatonin production in your body, If you have more melatonin and serotonin, then generally insomnia is improved. The current drugs on the market for insomnia have lots of side effects and are not very effective over the long term. So research into probiotics to treat this condition is definitely worthwhile. Next slide, please.
All right, so these are the 30 states that we used for our network simulations. On the left side in the pink, you can see all of our states for the bacteria that we're researching, the various neurotransmitters like cortisol, serotonin, melatonin, states for insomnia and stress. And on the right side, in the blue and the purple, we have our adaptation states that correspond to our neurotransmitters and stress to better reflect neuroplasticity. So in the blue, we have adaptation states for connection weights, and in the purple, we have adaptation states for speed factors. Next slide, please. And here is our adaptive network model. You can see that it has 3 layers. The top 2 layers, the first order and second order reification levels, are our adaptation levels. Next slide. And here are the combination functions we used in our model. So the identity function was used for states that do not change in their levels, such as the stress, the external stress that the person is undergoing. Alogistic or advanced logistic sum is used for states that change in general. So this is used for the majority of our states. And Hebbian learning is used for adaptivity and our adaptation levels, such as the connectivity weight and the speed factors. And bounded growth, we use this for the states that represent bacteria because we wanted to better reflect how bacteria can often grow in the gut microbiome. Next slide.
So in my section, I'll be describing in detail which specific scenarios we decided to model in the dedicated software environment in MATLAB with respect to our domain, our intended expectations from the simulations we ran, and our final inferences from the graphs generated. For the sake of simplicity, we ignore the first and second order adaptive states for the purpose of analysis. So in our first state, we have low levels of probiotics and high levels of bad bacteria in the gut. So as we have achieved this by taking initial values for probiotics as 0, and for the bad bacteria in the gut, we have used the bounded growth function, and it starts from 0.8 as the initial value. So as we can see that we intended to look at the effects produced on the system state of insomnia, which is X15 state over here, and its corresponding effect felt as sleep deprivation, which is our X16 state, in the scenario of imbalance of bacteria, such that we have no probiotics, which is our lactobacillus and bifidobacteria, but there is high levels of bad bacteria, which are the pathogenic bacteria such as Clostridium perfringens, Staphylococcus, etc., that release toxins and or trigger disease in the system. So this scenario is what we term as dysbiosis. As expected, we can see that the X4 state, which is our immune cell, it increases, and to bring the level of bad bacteria in the gut down. This causes gut permeability to increase, where this bad bacteria then permeates into the bloodstream. EEC1, which is our first enteroendocrine cell pathway, which activates HPA1 axis, is not activated, but there is an effect that is felt, which brings the levels of cortisols up, and the perceived state of stress that is felt by the body, as we would have expected in the normal situation. Next, we have our scenario 2, where we have high levels of probiotics, but low levels of bad bacteria in the gut. This is the opposite of our first scenario. And we have done the same, where we have kept the bad bacteria at a 0 level throughout. And our probiotics, lactobacillus and bifidobacteria, show bounded growth. I'm sorry, I think my computer hanged. I'm sorry for. I'm sorry. Because of my low battery, I cannot share anymore. Can somebody share screen?
I can share this screen. Just give me 1 second.
All right, thank you so much. Our intention in this situation was to find how the bacteria react in independent situations where they're not reacting with each other at the same time. So the first HPA state, which is activated by the lactobacillus, then acts, has a negative impact on the HP axis, which brings down the cortisol levels and the effect of stress, and in turn, the level of insomnia and sleep deprivation. In a similar manner, the bifidobacteria acts on the HPA2 axis, which releases serotonin, and it also acts on the tryptophan, which produces melatonin. This also brings down our insomnia and sleep deprivation levels and leads to the clock gene regulation. Next slide, please. So lastly, we have run a scenario where there's low levels of probiotics and low levels of bad bacteria in the gut, which means that we have kept all our bacteria at a level of initial value of 0 throughout the runtime. This leads to a state which is termed as dysbiosis, but this is not a usual situation because we usually have lactobacillus and bifidobacteria in the gut. But in case they are absent, the immune response is not activated. The cytokine response is triggered due to the constant external stressor factor, which is at a constant of 1. Throughout, this raises cortisol production, and the system then has, next slide please, the system then has a perceived state of insomnia, but lower than in the case of where there's bad or pathogenic bacteria in the blood as well. Next slide, please. So in conclusion, we'll be discussing some of the future perspectives that our model and our research could have in further research. So first, there could be bacteria in competition where good and bad bacteria both compete for food and resources to grow and proliferate in the same home environment, which is the gut, which then could have implications for mood and sleep. Next is real-world implications, where real-world situations such as night shifts or eating disorders or jet lag and such could be modeled. There could also be a 1-1-1 state where all the 3 types of bacteria are active and interacting in the same home environment. We have kept the external stressor value at 1 throughout. There could also be different external stressor values, which could then have their own functions for growth. There is also a strain of bacteria called opportunistic bacteria that unlike bad bacteria, do not attack the system immediately, but they wait for the immune system of the body to reach a low enough state, and then they attack and release cortisol, which then increases stress and insomnia. So I think our model and research was a simplified and organized effort into modeling bacteria present in the gut microbiome and their role on the overall mood, sleep-wake cycles, circadian rhythm, and any resultant sleep disorders in the person, such as insomnia. We are very happy to present at BICA. Thank you. Any questions, please?
Thank you, Sulagna, Claudia, and Kinley for your participation. Now we will proceed with the questions. If anyone has any question, please raise your hand, please.
I have a question.
Okay.
Hi. A system like this that you're modeling here is quite complex, and there are many chain reactions that are connected to each other. And my question is, how can you validate if the simulation data that you are generating with your model can be really what is happening in real life? Did you have a standard procedure for doing this validation, or you just simulate and need to believe in the what the simulation data provides you?
So we did qualitatively validate, but we didn't numerically validate because we have not yet found enough data to be able to do so on this topic. So what our model is based off of is just research papers discussing conclusions between the effects of like one hormone on a certain process. And then we built it up around lots of different research papers on these topics. So we would definitely need to numerically validate this model so that we would have a greater accuracy and make it more realistic. But that was what we could do with our time so far.
But it would be interesting, for example, if you, even on a qualitative way, if you can connect saying, okay, for example, study A and B reviewed the such and such kind of phenomena, and this is what is happening in the simulation. The other study provides such and such, and this is what we are having in our simulation, because this will give credibility to the model that you're building. So I think it would be a good suggestion to, even if you don't have a quantitative validation, you can validate it qualitatively by presenting the studies that you use to show that your process is doing what is expected to do. Okay, just a suggestion.
Definitely, if we had more time for a presentation, that would definitely be a good thing we could include.
Thank you.
Thank you.
Is there any other question? Okay, Howard, please.
Yes, hello. Hello, hello. Hi, Ricardo. It's nice to hear you. I don't think I can see you though. I thought that was a good question. It's an interesting topic, the probiotics. We've known for about 20 years that they're quite effective there's double-blind controlled studies now for depression, for insomnia, for irritable bowel syndrome, which actually is part of psychiatry. So, a lot of psychiatric issues, but also for colitis, Crohn's disease. But somehow it hasn't made it into mainstream medicine just because it takes so long. And I guess there's, there may be not as much profit potential as like in other pharmaceuticals. However, but there, I think your question, Ricardo, is a good question. It's so hard to actually do trials, which is why, it's not part of mainstream medicine. If I see people that have depression and I give them antidepressants, that's great. If my recommendation was probiotics, people would say, what's going on? But I think the problem is it's really hard to do the studies, although I think it'd be interesting doing meta-analysis. People have done it in other fields. There's somebody, Cipriani, who's done it for antidepressants, comparing all sorts of situations, which it would just be too hard to do. The trials cost many millions of dollars to start figuring out what's going on. But I thought it was a good talk. I thought it was interesting, a nice system that may have some utility. A very nice talk.
Thank you. Yeah, I agree that this could be taken a lot further. We just need to find, some good amount of data to be able to progress our model on this. But it's a really interesting topic, I agree.
Yeah.
Okay, thank you for your presentation. We will continue with the next presentation. Cristina Metova, are you ready?
Yes, I'm ready. Just a minute.
Okay. You have 50 minutes to present your work.
Yeah. All right.
Cristina, you can begin, please.
I'm sorry?
You can begin.
Okay. Hello, dear colleagues. Let me introduce our study, bold signal changes in response to pseudo words after giving them semantic meaning in the course of special training. This is fMRI study. The study was carried out on the National Research Center Kurchatov Institute in cooperation with St. Petersburg State University. To determine the bold signal in response to pseudo-word stimuli in order to show the involuntary attention system activation, as was done in previous electrophysiological studies. A passive multistimulus oddball paradigm, specially developed and adapted to fMRI, was used. In the course of special training, the meanings of the words of a hypothetical language were assigned to the stimuli. Changes in hemodynamic response parameters resulting from training were analyzed. It was assumed that learning and semantic meaning of the assigned words of the hypothetical language would influence the hemodynamic response change. The fMRI study involved 17 conditionally healthy, well-hearing subjects without neurological and mental disease, with leading right hand, aged 23 to 35 years, native Russian language speakers. Before the fMRI session, the participants were instructed and written consent was obtained. Scanning was performed on 3 Tesla magnetic resonance tomograph with 32-channel head coil. The participant was positioned in the fMRI chamber in the supine position. The head was fixed with C-link models for hearing protection, communication with personnel, and presentation of stimulus material. The non-magnetic headphones were used. The scan option you can see on the slide. A passive multistimulus oddball paradigm, especially developed and adapted to fMRI, was used, as I told. Stimuli were presented in blocks, 22 blocks with deviant 1 and 22 blocks with deviant 2. The block paradigm was used firstly due to the fact of response generation to a deviant stimulus that required a relatively short interstimulus interval. And in that case, the possibility of a sensory memory trace formation to the previous stimuli remained. Secondly, it was necessary to maintain the time required for attention of the hemodynamic response to the previous block. So the interval between blocks was 15 seconds. The block size was 10.5 seconds. Blocks were represented in a pseudo-randomized order. The fMRI session duration was approximately 19 minutes. During the recording process, the participants were instructed to maintain the most calm and relaxed state and carefully look at the silent dynamic image on the monitor screen to divert attention from auditory stimuli, which is one of the conditions for applying the passive oddball paradigm. A neutral screensaver was used to the image in which orange circles of various sizes flickered smoothly against the black background. The image from the monitor was projected by a system of built-in monitor. There was no need to pay attention to the auditory presented stimuli to access possible distortion and association in the perception of stimuli. After the study, the participants were interviewed. A little bit about semantization of pseudo words. After the first fMRI session, participants received the following homework assignment. Each was given a 14 minutes educational audio recording, which had to be listened to twice a day for 7 days. In these audio recordings, pseudo words were assigned the meaning of the words of hypothetical language, which differed in the frequency of use. Each pseudo word was repeated 45 the hypothetical language word of assigned frequency value. It's important to note that it was necessary to set lexical characteristics according to which stimuli would differ. For this purpose, lexical frequency was chosen. The word frequency was determined according to the new frequency dictionary of Russian vocabulary, the frequency dictionary of living Russian speech, and the national corpus of the Russian language. In order to fix the learning outcomes before the second fMRI session, participants were instructed to listen to the audio recordings again and then write at least 10 memorized suggested statements. The second fMRI session took place 7 days after the first one by the identical procedure. Results. The resulting mapping data were processed with the SPM12 software package on the MATLAB platform. The data were analyzed in the event-driven fMRI paradigm. It's worth noting the importance of correcting the temporal bias, since a significant temporal bias between slices occurs during the functional data collection. Statistical parametric maps of the participants' brain activity were constructed by the GLM. Data analysis was carried out in 2 stages. At the first level, analysis based on the calculated GLM parameters, the contrast between all types of stimuli, this is standards, Deviant 1 and Deviant 2, were calculated separately for each subject. The obtained contrasts, representing a linear combination of GLM parameters, were subjected at the second level analysis to further statistical group analysis of rare statistical hypotheses. T-contrast was calculated using the flexible factorial option, which corresponds to a 2-way analysis of variance. This is repetition factor and stimulus type factor. Data were statistically compared by the students' t-test. The SPM anatomy toolbox software package were used to identify brain structure and analyze active clusters. Significant differences were found in the right temporal gyrus. Figure 1 shows changes in the hemodynamic responses to deviant stimuli detected after training on the right side of the middle and superior temporal gyrus. Before learning, there were no statistically active areas in the right middle temporal gyrus, as you can see on figure 1A. They appeared only after training. You could see it on figure 1B. It's clearly seen that after the right in the middle temporal gyrus. There is a significant increase in the hemodynamic response intensity in the right hemisphere in the superior temporal gyrus. Several small foci of local activity observed before training at the junction of the visual association and temporal cortex disappear after training. If you compare figure 1A and figure 1B, you can see it. In addition to changes described above, there are differences in hemodynamic response in the left hemisphere. Figure 2 shows changes in bold signal in response to deviant stimuli detected after training on the left in the temporal plane and in the superior temporal gyrus. Figure 2 shows that after training, the signal intensity higher in the left temporal plane and in the superior temporal gyrus. Some additional areas of activity, like precuneus and angular gyrus, you can see it on figure 2A, which are observed during the pseudo-words processing before training, disappear after training. Figure 2B. The hemodynamic response to semantized pseudo-words is enhanced and concentrated in speech area. So it was shown that the response to different stimuli after training differed significantly from response observed before training, especially noticeable changes associated with the increase in hemodynamic response were noted in the right temporal regions, figure 1. Before learning, there were no statistically active areas in the right middle temporal training. After training in the right superior temporal gyrus, a much more intense increase in hemodynamic response was observed in comparison with the results obtained before training. The observed bold response to pseudo-words was much stronger than to the same stimuli before training. The right-sided activation on temporal areas when using the oddball paradigm was associated with the involuntary attention activation mechanisms and was well reflected in auditory event-related potential by the mismatch negativity appearance. Previously, it was shown that mismatch negativity parameters differed markedly when presented as different stimuli with words and pseudo-words, as well as in the case of using words of different frequencies. Moreover, if we use the semantization procedure, assign pseudo-words the meaning of the word, then after training, a pronounced change in mismatch negativity was observed, an increase in amplitude and decrease in the peak of latency occurred, and these changes were much more pronounced for high frequency words. Our data also showed an increase in response in the temporal areas of the right hemisphere. It can be concluded that after acquiring a semantic meaning, pseudo-words caused a significantly greater activation of the involuntary attention mechanisms in the oddball paradigm. The marked changes in hemodynamic response were all the more interesting given the moderate level of training and the short duration of training procedure. Also, it was found that after pseudo-words acquired the meanings of the certain hypothetical language words, changes were observed in the left hemisphere speech-related region. Noticeable differences were localized in the temporal plane and in the superior temporal gyrus. First, there was an increase in the reaction intensity. The hemodynamic response after training was shown to be enhanced in the temporal plane and in the superior temporal gyrus on the left hemisphere. And secondly, there was a change in the activated area distribution and some minor foci of local activity disappeared. There was an increase and concentration of the hemodynamic response in the speech-related region. It can be concluded that the stimuli semantization leads to certain changes in the functioning of speech-related region in the temporal cortex. This observation significantly complements the results obtained early in the study of semantization effect of auditory event-related potential and mismatch negativity. The auditory ERP method in this situation is less sensitive. The data obtained show that after the pseudo-word semantization, the significant differences in bold signal are found not only on the right in the areas, but we associate with the attention mechanism activation, but also on the left in the classical speech areas. An increase in hemodynamic response intensity is observed on the left in the temporal plane and in the superior temporal gyrus. Thank you for your attention, and I'm ready to ask your question, to answer your question.
Thank you, Cristina. Now we will proceed with the question. Are there questions? Please raise your hand. Questions?
Okay, I'm Felix, and I have a question. Christina,
yes.
Your experiments, or rather from your experience or your experiments, can you conclude something about a circuit for your...
About what? I didn't hear.
Sorry?
Could you repeat, please?
Okay, yes, sorry. I want to know if from your experiments you can conclude a circuit or something like that.
Conclude about what? I'm sorry.
A circuit, a way the input is processing or is processed through all the brain areas you describe in your presentation.
We found that areas that could be involved in involuntary attention appears like in ERP methods in fMRI. It's right-sided temporal areas. And second, we found that special speech regions activated when our pseudo-words get meaning.
Okay. Thank you very much.
Thank you.
Thank you, Christina, for your participation.
Thank you.
Good day. My name is Gustavo. So I will be the chairman during this new presentation block. We shall start with Howard Schneider's presentation, the navigation map-based cognitive architecture, a new class of artificial intelligence. Howard, are you ready to share your screen?
I'm there. Can you see my screen? Can you hear me clearly?
We can hear you. We can see your presentation. So you have 15 minutes to present your work. That will be followed by 5 minutes of questions from the audience.
Perfect. I will start. And again, hello to everyone. It's nice to be at another BICA conference. I'm Howard Schneider from Toronto, Canada. Let's see here. I'll be talking today about the navigation map-based cognitive architecture. And these two words, navigation map, nothing fancy. Think of a map and a type of cognitive architecture. And the theme of my talk is this is really a new class of artificial intelligence. There's many ways to achieve intelligence or natural intelligence, artificial intelligence. This is a differential analyzer. A number of them, large ones, were built in the 1930s, 1940s. They could do solve differential equations, do integration. And, if an electronics industry hadn't developed, probably people would have made inventions or been more cogs, more gears. And, as the years went by, this would have done more of the things that, that computers can do for us now, although, they are quite large. There are really two main ways that people use to make systems intelligent. There's symbolic logic, GOFI, good old-fashioned artificial intelligence, if then, if this, if then, neural networks, and there's a variety of them, artificial neural networks, spiky neural networks. However, today I'm going to be talking about navigation maps, and I believe this is what our brains, what the brain of a mouse uses to operate. Over the years, people have realized, no, brains really don't do what neural networks do. And many years ago, people thought, oh, they're like symbolic logic. They certainly aren't. Okay. What's a navigation map? Again, nothing fancy. This is before there was GPS and people wanted to go on a road trip. The Automobile Association they had all these maps, thousands of them, and they put them together bind them together, and you would drive from this city to that city. And when you got to the edge of the map, you could flip it and then go to another map. So they might give you 20 navigation maps. And basically, that's all I'm doing. This is the basis for my architecture. Except I'm doing it in Python, NumPy, not, it's a bit easier than paper. Every module in the architecture, I've been presenting these architectures since 2018 at the BICA conference in Prague. Every module in my architecture uses navigation maps, not just for navigation, but for everything. Why am I doing this? You look at the animal world. Invertebrates, with their tiny little brain, they have some sort of navigation system. You look at vertebrates, they all have navigation systems similar to the mammalian hippocampus to some extent. Hippocampus, it's a structure in our brain. In human brains, it's on both sides, it's about 40 to 50 millimeters. And fantastic research was done in the 2000s that we figured out, really well how a system of the brain works, grid cells, place cells, and it could explain how a rat navigates. But also, a lot of models started emerging that not only for navigation, but the same techniques that we're using to find a path between this point and this point can be used for memories too. This example, spatial cognition exists in fish, not just mammals. And again, from a genetic point of view, there's homolog genes in this little part of the fish's brain compared to our hippocampus. So the assumption of this architecture is that navigation map-like structures are behind all of our cognition. And given, it's not that surprising given the way evolution works, gene duplication, similar circuits probably got duplicated into our cortex. And again, that's my postulation. In terms of evidence, there's some, that's starting to emerge in terms of the genetics, but basically the postulation behind this architecture I've been working on the last 5 years is that every circuit in our brain, the higher level of the cortex, these are navigation circuits, but they're not used for navigation, they're used for everything. And this is the Causal Cognitive Architecture 1. I presented variants of this starting in Prague in 2018 at the BICA conference. And it's very different than building a different type of neural network or a different type of symbolic system. If you're working on a symbolic system, there were in the 1990s, when you said AI to somebody, they thought expert system. And, you can use just any language to do it. There were frameworks, expert systems. Neural networks have been around for a while. However, 2010, they won that ImageNet contest, and they really have taken off since then. And they've done amazing capabilities over the last decade. There's good frameworks, PyTorch, TensorFlow, Chris Elias-Smith in terms of spiking neural networks. However, these things don't really apply that well to navigation map-based architecture. It really is different. There's honestly, the navigation map-based architecture is neurosymbolic. There's symbolic elements and connections elements in there. So what I've been doing is playing with these networks, building small models in Python, playing with them. And what I found interesting, if I took the intermediate results from the central navigation module, and I fed it back to the sensory system, then it could be the next cognitive cycle, it would be treated as a sensory input and would be operated on again and again and again. And what happened is causal behavior emerged from this. My coding is just to simulate these structures, and this would be easier to do. You have some extra neurons making pathways. It's just another pathway. And lots of feedback pathways in mammalian brain. But also at the same time, you're going to get interpretation of some of these results as real sensory features. So you get psychotic features, in other words, hallucinations, delusions. And then you look at humans, which my architecture is based on. And in fact, 1% of the population has schizophrenia, but up to 17% will have some psychotic-like reaction at some point in their life, associated with the depression, with bipolar disorder, with another type of stress. And animals, they almost never get psychosis, and they don't have causal behavior either. We do. This experiments with chimpanzees proving pretty well that they really don't have full causal behavior. So what am I doing? I'm not using PyTorch. I'm not, using if-then statements. By feeding back these pathways, this wonderful property, causality, emerges from this system. Then it worked for toy problems. There were other problems. I presented this at a previous year's BICA conference. There was an issue with the binding problem, which it's an engineering problem. It's not a philosophical problem. And how's it solved? I solved it with, again, navigation maps. I can copy, I call them nav maps, navigation maps. And a navigation map is just this. Think of that map I showed you. And I can, mathematically, I can use linear algebra because it's an array. I can copy navigation maps. I can compare nav maps. I can add maps. I can subtract maps. Very simple operations, simple arithmetic array operations, very simple algebraic array operations. There was also an issue with the binding problem, a temporal binding problem, which the philosophers don't talk about, but which emerged when I built the system. How was it solved? Again, I realized, I can put a vector on my navigation map, a motion prediction vector, and I solved, so I presented the other year CCA3, the third version of the causal cognitive architecture, which was binding time, binding space, and had causality. And again, all by just manipulating these navigation maps, really a different type of AI. In the last year, I found that if I fed back navigation maps to this system, and then I subtract something, add something else, I get full inductive analogic reasoning. I will be talking about this in 2 days, and I think it's 10 o'clock the talk. I hope some of you are in the audience interested in this. I'm basically, these equations, they're just really, they're matrices because I'm dealing with arrays and dealing with the navigation maps, but copying navigation maps, moving them around, I get it, inductive analogic reasoning emerging from the system. I'll cover that. So basically, and then once I have analogic reasoning, which I will show at my talk in 2 days on the September 24th, you end up getting a full solution to the simple grounding problem, which turns out to be an engineering problem and gives a system very nice problem solving abilities. And I'll show a nice example on that. But the point is, by copying navigation maps, comparing, and again, when I say navigation maps, think of that map I showed you, like the road map. Copying navigation maps, comparing maps, adding maps, subtracting maps, adding some vectors to them, matching navigation maps, doing a feedback operation, and I get these wonderful properties coming out of it. My causal cognitive architecture really is just one of many possible implementations, what I call a navigation, again, think of navigation map-based cognitive architecture. In the paper that's associated with this talk, there's a long list of properties it has, the existence of navigation map-based like structures, the ability, I won't go through all of them because it's in the paper, but they have properties. There's properties of neural networks, properties of an expert system, symbolic logic. This has its own unique properties. A navigation map-based AI. Then I went through the entire Russell and Norvig. That's most of you may be familiar with it. It's a very common textbook on AI. I actually used the 4th edition, which just came out. And I compared it. I went through like Russell and Norvig, talk about logic-based agents in a chapter, and I compare it to navigation map-based architecture. That's in the paper also. I go through a long list of all the chapters. For example, deep learning, and I show how the navigation map-based architecture, it's different. It's not deep learning, very, very different. So again, the theme of my talk, navigation map-based cognitive architecture, it's a new and really represents a different class of artificial intelligence. In Russell and Norvig, they cover it's about 1,000 pages. They cover every field in AI, although cognitive architectures only have one paragraph, unfortunately. So let's look at the work done by Laird, Labier, and Rosenblum. Just like in physics, there's a standard model of physics, which has worked really well for all these messy details of physics. It puts it all together. Very nice, the standard model of physics. Might be changed eventually. It hasn't been changed yet. It's been holding up pretty well. Laird's standard model of the mind, it's pretty much this. There's a working memory, there's declarative long-term memory, there's procedural memory. And, they Laird, Labier, and Rosenblum, they show most of the cognitive architectures will fit into the standard model of the mind. Although, again, for the architecture I showed you, the CCA3, CCA5, which is the causal cognitive architecture, which works on navigation maps, it really doesn't. For example, the declarative, in cells within a navigation map, I have declarative elements, I have procedural elements in the same place. I've got issues where I'm moving maps around for the binding issues. I'm moving maps around for grounding. So honestly, it doesn't even fit into to their standard model of mind. So again, my conclusion that navigation map-based cognitive architecture, I believe it represents a new and different class of artificial intelligence and cognitive architecture. Thank you very much.
Thank you very much. So now we will proceed with the questions from the audience. So if anyone has any questions, please raise your hand. Okay.
Hi, Howard. This is Ricardo here. I'm not appearing in the screen because I'm here in Guadalajara in the audience. So that's the reason my name is.
It's nice to hear you, and hopefully next year I'll see you in person.
Howard, it's interesting. I like very much your presentation. I'm eager to see the next presentation with the details. But my question is related to how we create maps. Whenever I am driving in a road, for example, or in not a street or a big road, there are many details that will not appear on the map because they are not important. So I will be concerned, for example, with some exits, some ways of changing to a different road, or to particularly important things that should be appearing in the map. Okay, so my question is, when you talk about map navigation system as a general kind of cognitive architecture, a new paradigm for artificial intelligence, how are we supposed to make this triage of what should be in the map and what should not be in the map? So the question of how we construct our map based on the perception that we have of the world, because clearly we are dropping out many of things that are unimportant, and we will need to have other features that are important. So it's not just navigating on a map, but how we construct the map based on our perception of our environment.
I think that's an excellent question, Ricardo, for two reasons. The first reason is in terms of, memory, putting details on maps. One reason I was inspired by this, like in the 2000s, there was a lot of good work, eventually culminating with the Nobel Prize in this area, because we figured out how part of the brain worked. But very good work showing that it's not just about finding paths, but it's about memory. This circuit, it's really, responsible for how we make memories. So excellent question, and one of the reasons for my motivation in it. The other issue, more direct answer, like how we make it, I formalized my system much better, because you can't really give somebody 5,000 lines of Python code to look. I submitted a new paper for Cognitive Science Research Journal. I don't know, it's so long, I had no choice. There's so many equations in it, but it shows actually how I'm parsing out information and what information I'm putting in. Most of the information does not get put into the map. And here's the thing. One thing that also struck me in terms of brain functioning, we really do not, we see things with our eyes, and you would think, oh, we're putting megabytes of information into our occipital cortex. We're really not. It's the data flow isn't that much. I think to a large extent, what's happening in humans is we already have, forget about all the theories of the mind and all these neural network things, just listen for it's maps. Basically, we have maps in our brain. I already have a map in my brain. I know what to expect. I know what's finding. If there's differences between the map I have and what I'm seeing, then I'll just put some small variations, and it depends how important those differences are. And what I'm saying, actually, I formalized it in 106 equations in a recent paper I submitted, which became a bit longer than I wanted. But it's an excellent question. And how you actually handle those details, it will depend on other factors. There's a context matrix I'm using. There's an emotion vector. It depends what you're looking at. But it's an excellent question. The third question, which you didn't ask, but which probably you're thinking about, how can this be used in a practical way for robot navigation, an area that you're expert on, you do work on? And I'm not sure at this point it really could be, because at this, it's really a theoretical idea I have, and it's starting to get, but the point is, it's not about making robots navigate this. It's really about, how does the brain work, and how, really, how can we make, like, eventually an AGI? But once you have that, navigation works much better. It works much better than, say, in a self-driving Tesla or one of the other cars where, basically brute force and neural networks matching things. Here, I can send you a preprint of my paper if you'd like, and I can show you some of the code. It's an excellent question because you can't put all the information into the map, and it's very small amounts of the information actually are being put in the map. I don't know. Does that answer make sense? I just gave.
Yeah, my point is that we cannot go too much further just with a grid map, because if we go to a continuous world, we have an infinite number of grids, of cells in the grid, and it will be unfeasible to put that on a computer. So we need to have a way for discretizing that in a different way. It cannot be a grid map. It needs to be a kind of a topological map. We're just putting the parts that are important, and then maybe using some kind of vector logic for doing that. But the real point is how to discriminate, how I will decide that something needs to be on the map and the other things I am just going to not pay attention with the details because they are not important at all. But
the way I discriminate is there's already an existing navigation map in the memory, and it'll compare it to what's there, and it'll actually, just like humans, it'll ignore a lot of things. It's not that open to new ideas. It's expecting to see certain things, and if it's expecting to see it, the action will be taken. It's sort of tricky in terms of when do you pay attention to stupid little details, which a lot of times it'll miss, just as humans miss it. Because I think we're using the same system. And I agree with you. It's not you can't have an infinite system. But I don't think you need as much memory as people think you need to do this. With the navigation maps, you can get by probably with a lot less information. In terms of the maps, they actually are, the hippocampus probably is three-dimensional. There was somebody in Israel doing work with fruit bats, I forget his name, and showing the three-dimensional structure of the hippocampus, like with the bats navigating. So we even though it's two dimensions, the neurons, it's a sheet of 2 dimensions, but actually there was a paper published a few years ago, interesting three-dimensional representation. You can do three-dimensional representations. The brains of animals, they're not that big, and somehow they managed to encode all the information. I think the important thing is what you're encoding, one, and two, how do you process it? If you have a neural network for self-driving, you need massive amounts of information. It's pretty brute force and pretty stupid. On the other hand, here, if you're starting to interpret things, I'm saying with the navigation map, you may not need as much data as you're saying. It certainly doesn't have to be infinite. It can certainly be discrete chunks that might be larger than you think. But I wish I was in person. It'd be fun to have a coffee and talk about it, to show you.
Okay, we have one question from Alexei.
Oh, thank you. Hi, Howard. Nice to see you. And thank you for the interesting talk. Actually, I absolutely agree with you that maps play the key role in the brain at all levels. I would not say that navigation plays the role at every level. And actually, I was a bit surprised when you declared navigation maps a new kind of intelligence or a new kind of AI. You also mentioned the book of Russell Norvig, in which I believe they cover navigation substantially. And it is actually a part of classical AI. Navigation and planning are parts of very classical logical AI, in my view. Well, unless you propose a completely different approach, but navigation is now considered a solved story in AI. So there are no new research coming on navigation in AI. And also, you didn't mention how you do it. You were just talking. I'm very, very interested myself in your algebra of maps. How do you define it? What does it mean to add, to subtract two maps, maybe multiply and so on? But still, I do not know how you actually use them and what's the key idea that makes it a new kind of intelligence. Maybe indeed there is something absolutely new, but we didn't hear. Well, I guess there was not sufficient time to describe all details. So yeah, my point is that navigation and planning are classical fields in AI, and in most parts they are considered solved already. So why call it new kinds of intelligence? Yeah.
I think that's a very interesting question, Alexei. You know, I agree. You know, pathfinding has been part of classical AI since the 1960s. You know, people were writing Fortran programs for it. Yeah. However, actually, I think you did work in this area. I think with Dr. Ascoli, 2005.
Also with Professor McNaughton.
Yeah, and with Nadell.
Because, actually, from that experience, I can tell you that hippocampus is definitely involved in representation of space, but it is there is no proof that it is involved in navigation. Navigation itself may be solved by different parts of the brain, actually.
Yes, but again, as I was mentioning to Ricardo, I'm actually not that interested in physical navigation. Let's say using this for a robot to navigate, or using this for a self-driving car. What I think the exciting thing is, it's navigation of memories.
Yeah,
it's navigation of memories. It's and that is such an important idea. And I know that, you know, the Nobel Prize was given to 2 people, but there were a lot of people, like including yourself, that did great work in the area. You know, it wasn't just one person; it was a number of people. The ideas came together, and I think, you know, in terms of the AI, certainly like in medicine, psychiatry, the ideas I'm saying are crazy. No, but it's not part of medicine. We know what the hippocampus does. We know it's, that's been known for so long also. But in terms of, but what I'm saying is that our whole brain, everything, it's navigation, but not navigation of a street, not navigation of a warehouse, navigation of memories. And in terms of how I'm doing it in the paper, which I recently submitted to Cognitive Science, it went a bit longer, but I tried to explain every operation clearly. I put lots of tables. It ended up being, I'm ashamed to say this, it was like 68 pages, which, but that's with the tables and illustrations. The text's not that long. You know, I'm expecting to say this is too long, rejected, but I tried to show very, very clearly there's nothing magic I'm doing. And I'm basically, does the brain do the exact same thing? Certainly not, but I think overall it probably does. I think the it just, because again, maybe it does other things, but I started building these models in 2018. I presented the first one in Prague, and which I'm really grateful for the BICA, having a place like BICA to go where other people are interested in this, and you know, and then properties started emerging that, you know, it's what we see in humans. Hey, psychosis, why don't other animals have causal abilities? Why don't other animals have psychosis? You know, it comes out of the maps. You start seeing the binding problem. It comes out of the maps. The grounding problem, which is a big issue in AI, it's not an issue in this network. It almost emerges immediately. Solutions emerge like perfectly because of the navigation maps. You know, again, and it's the postulation, which, you know, I guess you agree with, is that the hippocampus and navigation of memories is it's behind our brain, and I believe it really forms a different type of AI. And I'm surprised more people don't really work on it. I know navigation it's a whole field. There's self-driving cars now. It's a huge industry, but I think they think it's something different.
Personally, I like the term semantic map, not navigation. Okay. And I'm not sure that you are really using algorithms of navigation in solving memory problems. Well, we did in our work with Ascoli, you're right, you pointed to that. But I do not know how this could, well, so it's just a question of terminology, in my view, because some people may be upset when you talk about navigation as a new kind of AI. Not me.
Fair.
Okay.
Yeah, fair enough. I know it's been around since 1960. You know, before I was born, it's been around. It's been around for a long time. I know. Yeah.
Thank you.
Yeah. And it was nice to see you, and nice to.
But yeah, nice to see you. Nice to see you.
Okay, so the time for questions is over. If anyone in the audience has any more questions, please contact the corresponding author directly. Now we will proceed with the next talk given by Suhas Kalian. Sorry if I mispronounced.
No problem. Great. Thank you. Let me go ahead and share my screen. Howard, if you could relinquish sharing your screen, then I can share mine. Thank you. Okay.
So you will have 15 minutes to present your work, followed by 5 minutes of questions from the audience. So whenever you're ready.
Yes, yes. From beginning, slideshow, share. Okay, are you able to see my my screen?
Yes.
Great. Okay. All right. So this talk is entitled "Robust Classification of Contraband Substances Using Long-Wave Hyperspectral Imaging and Neuromorphic and Full Precision Convolutional Neural Networks." This is joint work with Congshape Park, now at Amazon, Jeremy Forrest, now a postdoc, Sudipto Chakraborty, my colleague, James Daly from Bodkin Design and Engineering, myself, and Srinivasan, the CEO of Quantum Ventura. Srini is the corresponding author. So to give some introduction, this is about detecting contraband that flows through borders. So contrabands are illegal threats that pass through customs and border protection ports of entry. And there's several agencies which seek to stop this flow of illegal material, such as the Department of Homeland Security. The Department of Homeland Security created a SBIR, Small Business Innovation Research Grant, and they set some very difficult metrics to achieve. So a hardware-software solution, portable, non-ionizing, that means no neutrons, no X-rays, handheld, cost less than $50,000, that can be held by a person or have containers moving under it at 4.5 meters per second.
Sorry to interrupt you. You're sharing the author's
yeah, okay.
view.
Yeah, okay. This always confuses me.
On display settings, you can change
yeah, okay.
the presenter. Yeah.
Is this
Thank
better?
you very much.
Okay.
Yes.
Okay, great. So as I was saying, very, very difficult metrics. So we partnered with Bodkin Design and Engineering, who are hyperspectral imaging experts, to design a high throughput non-ionizing screening capability in long-wave infrared using CNNs, or convolutional neural networks, implemented on both full precision and reduced precision neuromorphic computing. So this is the information on the hyperspectral imaging. So the illicit materials that DHS and other people want to detect have unique absorption spectra in the long-wave infrared bands, as opposed to the mid-wave infrared or short-wave infrared. So that's where we focused our energy. So what you'll see on the top is methyl salicylate, SF96, fentanyl, and VX. VX is a nerve agent. The others are basically illicit drugs. And then on the bottom, you'll see, benign materials that might be the backgrounds, like lignin, which is a major part of cardboard, plastic, and polyester. Polyester is often used in clothing. So, we were able to find the spectral signatures of the contraband, but that's pretty much it. So we had to then create code to create synthetic HSI, or hyperspectral imaging, of arbitrary chemicals with different backgrounds, different temperatures, and different purities. So that's, we created this new custom code to do that, to go from these spectral curves, and then we can arbitrarily change those three factors I just mentioned. So furthermore, we synthesized 27 hyperspectral imaging data cubes. A data cube is something with 2 spatial dimensions, X and Y, and then the 3rd spectral dimension, which goes along the wavelength. Each data cube had 3 contraband chemicals side by side at 3 specific temperatures and 3 specific coverage amounts of purities. 3 times 3 times 3 is 27. The data cubes consisted of fentanyl, methyl salicylate, and SF96 on 3 different backgrounds. Like I said before, cardboard, plastic, and polyester for clothing. So you can imagine a border control agent scanning some substance, let's say it's on cardboard. They don't know whether it's benign or illicit, or illegal or illicit. So that's what we're trying to set up, is the machine learning system that can detect contraband and distinguish it from non-contraband items. The 3 temperatures we looked at were 5 degrees Celsius, 20 degrees Celsius, and 35 degrees Celsius. This is to simulate cold room temp or moderate temperatures and hot temperatures, which you might encounter along various borders. Coverage amounts varied from 100%, 50%, and 25%. Just proofs of concept. Later on, we could expand the range of the temperatures and the coverage amounts, and then also change different contraband as well as background material. 20% of the pixels were used for training and 80% used for testing. And then in terms of the machine learning model, we use something called a spectral spatial residual network, which is a special type of CNN, convolutional neural network. You'll see it on the right there. On the top is spectral feature learning, so it's mixing several bands and using a ResNet type skip connection to learn what's important information to fuse across the bands. And then once you do that, you can then do spatial feature learning on top of the spectral feature learning. In this case, you're looking at overlapping spatial regions, and then finally you can do max pooling and classification through a fully connected layer. So this we implemented on a GPU, which has full precision 16 bits, but also reduced precision on these neuromorphic processors. And so this SSRN, spectral spatial residual network, takes raw hyperspectral data cubes as inputs. So there's 7 by 7 patches, spectral patches, and spatial pixels, and then 61 spectral bands. And again, the goal is to detect contraband versus non-contraband. So this is the neuromorphic convolutional network. Neuromorphic processors implement CNNs with reduced size, weight, power, and cost compared to GPU versions. We had early access to BrainChip, one of the vendors in this space, SDK, and that's where we focused our efforts on using BrainChip. We now have access to the Intel Neuromorphic Research Consortium and are using that for other projects. BrainChip, like Intel, can support many features of CNN, but not all. So for example, we had to remap the 61 bands of the hyperspectral image into separate grayscale inputs and then fuse across collections of input channels. So you'll see in the upper left, we take a 7 by 7 image patch of channel 1, and then we do that for channel 2 through 3, 4, 5, 6, 7. We glom all of those into one kernel, and then similarly for 3 through 11, 5 through 13, and so on. So then we're fusing across spectral bands there in the top, and then with skip connections for the ResNet, and then on layer 7 we transition from spectral feature matching to spatial feature matching. So now the size of the spatial kernels is much larger. Okay, and so that is, this is how we remapped the full precision convolutional network into the reduced precision neuromorphic architecture, which doesn't have, as many features, but has smaller size, weight, and power. Okay, so here are some results. This is the simulation of the hyperspectral imaging spectra. You'll see in the upper left fentanyl citrate at one temperature and then another temperature. And then you'll see on the blue curve, which is fentanyl, at 11 nanometers, it's gone down in emissivity. And then on the right, you'll see fentanyl on two different backgrounds. The green curve, polyester versus lignin, a major component of cardboard. And in this case, if you go from top to bottom, the emissivity has increased. So this was the ability to model the different contraband chemicals at different temperatures and different backgrounds and coverages. Coverages is not shown, that's in the paper. And then we have these spectral curves, and now we want to simulate what they might look like in an image from a hyperspectral imaging camera. So to do that, we're sampling these curves with a normal distribution and some camera noise. And that's what you see in the bottom parts. You have a lignin background at one temperature and one wavelength, and then the three contraband materials. And you'll see that the third contraband material, SF96, looks a lot like the lignin background at this wavelength. And then on the right, you have a polycarbonate or plastic background at a different temperature and a different wavelength. So there's 61 of these. Let's take the left image, lignin background. You have 61 different images like this for one temperature and 61 different wavelengths. And then same for the right. And in total, you have 27 images. So different temperatures, different backgrounds, and different coverage amounts. Coverage in this case means the contraband is not pure, but some of the background is showing through the contraband material. So the full precision GPU convolutional neural network got pretty good results, or promising results: 64% for fentanyl, 60% for methyl salicylate, and 81% for SF96. So you'll see on the right there some accuracy as a function of background and accuracy as a function of temperature. And then in the paper, we have accuracy as a function of coverage amount. So overall, 71% accuracy across different backgrounds, 70% across different temperatures, and that's pretty good. The neuromorphic convolutional neural network, we used a slightly different data set and found some performance decrease relative to the full precision model. Full precision got 70%, 86%, and 75%, whereas the neuromorphic convolutional neural network got 65, 56, and 55%. And this is somewhat to be expected. You're using a reduced precision model, and it wasn't a direct translation of the network. But we're looking into improving the ability to translate from full precision to reduced precision in another project, and I'll describe that other project in my next talk. So the discussion and conclusion, we demonstrated proof of concept of high throughput, non-ionizing screening capability using long wave infrared hyperspectral imaging and convolutional neural networks. And with good accuracy, this combination of techniques can detect and classify contraband in a range of situations. And also the neuromorphic computing implementations offer promising results with much lower size, weight, and power. As you probably all know, a GPU is pretty large, whereas these neuromorphic computers are roughly the size of a thumb drive, using milliwatts of power rather than 150 watts of power. Also, the price is expected price is much larger. GPUs can be thousands of dollars. These neuromorphic computers are expected to be less than $100. Okay, so there was a decrease in performance comparing the full precision to the reduced precision, likely due to the limited precision of weights. And hyperparameter tuning is something that can be used to mitigate this effect. Some areas of improvement or potential ways of improving the research. So, for example, on the sensing end, compressive sensing can be used to reduce the size, weight, power, and cost of the imager. In terms of the HSI, hyperspectral imaging synthesis, as I mentioned before, there isn't a lot of data out there, so you have to synthesize it. We used one method, but generative adversarial networks is another method to do it, provided you have a good amount of data to bootstrap that process. And as I mentioned before, our full precision and neuromorphic CNN results are preliminary, and certainly we can continue hyperparameter optimization to yield better results. And with that, I'd like to conclude and thank the Department of Homeland Security for awarding this contract. It was a fantastic project. I'd love to take your questions.
Now we will proceed with the questions from the audience. So if anyone has any question, please raise your hand and I will assign you your turn. Okay, so we have a question here.
Is there anything in particular for using infrared for detecting these substances that you're doing, or any other kind of spectra could be used? I mean, why infrared?
Sorry, did you say far infrared?
Yeah, the kind of sensing that you're using in your system, as I understood, is infrared. Maybe I'm wrong.
Yes, long wave infrared. Yeah, so people use X-rays. Some people even use neutrons. Those are very large machines which can potentially see through metal, but they're also ionizing. So it presents a danger to the people within, in the car, the operators of the machine, things like that. People have tried, so I'm trying to remember the other methods, but long wave infrared is nice in that it is portable and non-ionizing.
Yeah, but I mean, this is maybe useful for some kinds of drugs or particular kinds of things that you may try to detect, but they might not be useful, for example, for cigarettes contraband, or for electronic contraband, or different kinds of.
Yeah, so for sure. I think the use case is a border control agent would open the trunk of a car or examine a suitcase, and certain things you can pick up visually, and other things you're not sure what it is, and then the human eye can't determine what it is. So, in that use case, the human eye can figure out this is electronics, this is cigarettes, but then it sees a white powder. It doesn't know that white powder is baby powder or fentanyl citrate, and that's where this long wave infrared might be able to detect the contents of that white powder.
Okay, thank you.
Are there any other questions from the audience?
Okay, fantastic. I'll go to the next talk.
Sure, thank you very much.
Okay, thank you. All right. Okay.
Could you please stop sharing?
Stop sharing?
Oh, I think that your next talk is in the other room.
Oh, okay. I go to the other room. Okay. All right. Thank you. All right. I log into the other Zoom link.
Yes. You use the other Zoom link, and that would be your room.
Okay, thank you. Thank you.
Thank you very much. Okay, so now we will proceed to the last talk of this block. That will be, well, the speaker will be Sergey Volkov.
Yes, hello everyone.
Hello.
I'm trying to share my screen. So
Okay.
can you see it?
Yes, now we can see it. You have 15 minutes to present your work, followed by 5 minutes of questions from the audience.
Okay, thank you.
Whenever you're ready, you can start.
Yes, so hello dear colleagues. My name is Sergey Volkov and the topic of my report, training multilingual and adversarial attack robust models for hate detection in social media. So let's start from topicality and purposes of our research. Nowadays, social media is the most significant information source and the most important communication tool on the internet. And information in this is in social media can be aimed at discriminating against some group of people, and such intolerance can provoke terrorist acts and even wars. So, and creating and studying methods for hate speech detection in social media is necessary to maintain public safety. Current approach to hate speech detection can be considered as similar to sentiment analysis methods. Globally, they can be divided into two groups. First group is lexicon-based approaches, and the second is machine learning approaches. Lexicon-based methods analyzes some text features, for example, terms presence and frequency, or parts of speech, analyzing or extracting opinion words and phrases that commonly used to express opinions, for example, good, bad, like, or hate, and so on. But in our research, we decided to use machine learning method, namely neural networks. We applied a huge multilingual model to solve the task of hate speech detection in different languages. Yes, if we are talking about machine learning, there is a large number of ways to cheat models that we used. And the term adversarial attack is used to describe the process of influencing a model, which can lead to incorrect operation of this model. So we decided to find out how such attacks can affect the results of hate speech detection. In our research, we used a few different data sets. Two data sets was used for fine-tuning training model, and for training the model we used Russian trained data set, which consists of social network comments that are classified as toxic or neutral, and Hindi trained data set, which also consists of social network comments that are classified as toxic or neutral. And for testing the model, we used two gold data sets with religious texts. For example, in Russian language, it is data with religious text with three hatred labels that were merged in one. Religious hatred, ideological hatred, and terror texts were merged. And the second golden set in English with religious texts. It has the same labels, neutral or hate. So this slide shows the distribution by classes for each data set. This is not a large amount of data, but we use an already pre-trained model, and this data was used for fine-tuning and testing model. Texts of each dataset were pre-processed before starting the experiments, since many texts are comments from social networks. So the following steps were done. First of all, removing emojis, removing hints in tweets, removing hashtags, replacing numbers with the mask, and also replacing locations and person and removing links. So the model we decided to use is XLMR model. A few words about this model. XLMR is based on Facebook's Roberto model released in 2019, and it is a large multilingual model trained on huge data and in 100 languages. And the model is capable of analyzing text no longer than 520 tokens. So, and this model can be fine-tuned just in one language and zero-shot transfer to other languages. How we implement text attack algorithm. Adversarial attack algorithm was implemented to Russian trained dataset and both test datasets. So this algorithm changed some words in sentences from the dataset to synonyms using word embedding model. Then universal sentence embeddings are used to evaluate sentence similarity. If our generated sentence are quite similar to original, then we append it to attacked dataset. So the modified word is converted to the same form as the original word. And we consider it three parts of speech, verbs, nouns, and adjectives. What about model fit pipeline? In our study, we considered three approaches to training models. First is getting baseline model. It is first step. We trained our XLMR model on mixed Russian and Hindi training data, and then testing it first of all on Russian dataset and attacked Russian dataset, and then zero-shot testing on English data. So the second version of the model is XLMR advanced model. It was additionally trained on attacked Russian training data. And the third one is ensemble of models. we decided to train this Ansible because some automatically generated samples from our algorithm can be incorrect, and to minimize this effect of noise, some errors, we fine-tuned an Ansible of models on Rust attack dataset using bootstrap methods. And the Ansible of models was also tested on all 4 test datasets. The result of the Ansible prediction is calculated as the maximum argument from the sum of the outputs of all models. So some classification results are presented on this slide. First of all, the base XML model shows good results for all test samples except Russian test adversarial dataset. It is attack dataset. So to fix it, we decided to fine-tune the model with the same training texts in Russian that we attacked by replacing valuable words with synonyms, and thus we got the advanced model, and we can see that score increased. And the next slide presents the same results, but in table view. And you can see that also algorithms for replacing words with synonyms for English and Russian are slightly different from each other. However, we can see that after fine-tuning on attack dataset, on Russian attack dataset, the accuracy on English data, on English examples, also slightly increase. Yes, this parameters. Okay, and conclusion. In this study, we have implemented and tested several simple training techniques to make cross-lingual hater detection model robust to adversarial attacks. The experiments show that using training data with adversarial attack samples in one language also improves the quality of classification similar cases in zero-shot language, in English in this case, and using randomized sensibles of deep models allows you to slightly reduce the test error. So that's all. Thanks for attention. Any questions, please?
Okay, so now we will proceed with questions from the audience. So if anyone has any question, please raise your
Hi, Professor Jinshu Wan.
Hey, hello.
Hi, Antonio.
Hi.
We will start in 2 minutes.
Okay, no problem.
one on the side, a PhD in computer science from the Nottingham Trent University in 1998, and has been a full professor since 1994. He is professor of cognitive system, brain science, software science, and intelligent mathematics. Professor Wan is the founding president of International Institute of Cognitive Informatics and Quantum Computing. His basic research has spanned across contemporary scientific disciplines of intelligence, mathematics, knowledge, robotics, computer, information, brain, cognition, software, data, system, cybernetic, neurology, and linguistics. So, Professor Wan, you will have between 45 and 50 minutes to present your talk, and after that, we will proceed with a question and answer session.
Okay. All right. First, I'd like to thank Professor Rammer's great organization of this series of conference. And also thank you for your colleagues for the organization. And so for this talk, I'd like to talk about the relationship between AI and NI. NI here stands for natural intelligence. We say brain inspired systems actually is based on understanding about the nature intelligence that's underpinning our methodologies and technologies for implementing AI and autonomous systems. So you say now we are touching something very, very fundamental in this field of work, because we are dealing with the fundamental level of intelligence science, the basic understandings about human intelligence, about the theoretical foundations of intelligence generation and implementation by machines that maps to the work in AI areas. And so this is the structure of my talk. So I'd like to discuss in session 2, I'd like to discuss the current understandings about AI, particularly what can AI do. So we see AI had implemented a number of good things, but the theoretical foundation of AI actually is quite weak. And there are so many fundamental things that current AI technology can do. So that's our opportunity to dig up, to seek foundations and the basic theories towards intelligence science and generic AI series. So based on that, so that lead to the brain-inspired systems. We call it, use the term, we call it autonomous AI, so AAI. So AAI actually says how the understanding about the brain in brain science and intelligence science would help us to understand the future direction of AI and how would we implement more powerful AI systems. So this is the rationale in this talk. So first look at the human intelligence. So human intelligence developed, you say, that's over several hundred million years actually, and we are actually all the development, we may summarize them as the development of human collective intelligence. So in the very beginning, in the very beginning, and actually the development of human intelligence actually is triggered by the emergence of languages among humans. This is about 500 million years ago. We have simple language, simple expressions, and then that lead to the current status. So it is, in intelligence science, many people believe the human intelligence was triggered by tool making, by collaboration and by many other factors. Actually, the language was one of the major things because that enabled people to think in an abstract way, and that enabled people to do symbolic-based reasoning. So all these things lead to another special language. This is a different kind of mathematics that give us the power to reasoning in a symbolic, abstract way. This is the beginning of our abstract intelligence, lead to the development to the industrial revolutions in England for for enable people working together for precise and mass production. And that enabled the organizational technologies nowadays we call it engineering. And also something I would mention is very important, I believe, is a car driving, it's a human driving. And you see all the other part is abstract intelligence. But driving is a very special technology part of our intelligence called real-time behavioral intelligence. It is a counterpart of the abstract part, and this is so important because this part of intelligence need us to handle decision making and external events at a level of milliseconds. This is unprecedented in human evolution because this is something require you have a very fast reaction by the brain. So the brain is triggered in the very beginning by language, but now a major part actually is by the real-time decision making and reaction. And this is also that, let me think, I would believe in the field, we are developing self-driving cars nowadays. I would think that's anti-development of human intelligence, because once you sit in a car without any maneuver, actually you lose the chance to develop the brain. The brain will get not that sharp because you do nothing there once you get a self-driving car. So I'm worried actually our next generation or next few generations will be affected by this. That means very important factors to trigger our intelligence as a whole would dismiss. So then that's not helpful for human. Just like we stop to talk, we stop to use in language or mathematics, that will reduce our power of intelligence. So that you say that lead to another level of revolution from the industrial revolution is the information revolution. So that's a trigger, the computer science, the internet, knowledge bases, all this help us to process intelligence, knowledge that lead us to the next phase. This is the current phase of intelligent revolution we're in. And that's lead to the understanding of the brain, develop brain-inspired systems, autonomous systems, cognitive systems, robots, and symbolic intelligence. That's human and machines, symbiotic human machine intelligence. This is the future. We incorporate machines into our decision making. So that will be more powerful, symbiotic human machine societies in the future. We are working actually interactively and coherently with machine in the future. Or we are going to use machines to augment human intelligence. And you see, this is all the trees lead us here. So that's why we say this year's conference actually address a very important issue and a very fundamental problems, and that will lead a very important development in the future. And so first, let's look at the basic ideas about what is intelligence, what is intelligence science. We say intelligence is generated by these small areas of the brain, and this is so important because that's help us understand what is intelligence. So here we say the theoretical part of intelligence we call alpha I, not AI. It is stand for abstract intelligence. We say the definition of abstract intelligence actually is in a narrow sense, it is a function. It's a behavior function that transforms information into knowledge, into behaviors. So anything may trigger the generation of intelligent behaviors. It is a kind of abstract intelligence. Whatever is the means, you would implement it, code by machine, by animals, by human, or by any other mathematical system. That's the same. We call it abstract intelligence. But broadly, there is another kind of intelligence in its a framework. It's called the knowledge generation intelligence. That means transfer knowledge. This kind of intelligence transfers information into knowledge. So put them together in parallel, we would say, okay, abstract intelligence actually covers anything, any mechanism. If that system may transfer information into behavioral knowledge, we believe that's a kind of intelligence, whatever is the means of implementation. And so that's a lead to a larger picture. The whole picture say we live in a natural world. But what is our position? Actually, we are in a center here to say we live in a parallel world. We have a physical world, that's the real world. But we have another world, it is an abstract world built in our brain. This world is much, much greater than the real world because we can cross the universe within a second or a millisecond because we have a very large model, abstract model to model what we understand about the external world. Excuse me. You see, we model the real world using two major metaphors. One is matter, one is energy. But we only have one metaphor to model the abstract world. It's information or symbolic things. But the driving power is alpha I, is our intelligence that transfer the things in between. Einstein had already told us the real world transmission between energy and matter in both ways, but actually there existing ways we abstract the real world things into our abstract world. And I use the line is not solid means the mathematical models had not yet fully developed. But here with Einstein had already told us how to do the transmission. So this is the whole picture that linked our human brains to the real world. So this is actually the essence of abstract intelligence. Another perspective is about the layers of human intelligence or intelligence systems power in different levels. We say the bottom level where we share with animals and simple machines is reflexive intelligence. And the top level is fully powered cognitive intelligence. So in between there are imperative, that's something like programmed or pre-stored intelligence. This is human after training or machine after training, they behave like this. And then we have adaptive intelligence. But somehow in the last 60 years in intelligence science, computer science, information science, we were bounded here, have no development or progress because our machines at this moment may only do something. It is relatively flexible and adaptive, but they are not autonomous. So our ultimate aim in AI and intelligence science is to enable the machines to generate their own intelligence, rather than we provide the machines by code or by train the situation at this level, and train the skills or by using a neural network, or by programming powers to enable something at adaptive level. Actually, this cap should be broken. We should reach here in the near future. We are doing this in intelligence science and all the cognitive systems and brain species, actually we're trying to break this cap, this bottleneck. So this is the whole ideas of the levels of intelligence and our current situation. We stay here too long. We were stay here too long, you know, for more than 6 years. Now we are trying to reach this level. Once we reach the top level, it is just like the power of human brain. So that's the full implementation of machine intelligence towards human level brain-inspired intelligence. So that leads to the need to study about the brain, because without understanding the brain, that's the biased and powerful intelligent implementations in a nature way. If we don't understand this, we really can't stand or can't predict what is the directions to improve the current AI technologies. So study about the brain may be divided into two parts. One is understanding the structure of the brain. The other part is understand the functions of the brain. The functions are built on the structures. So you see the brain actually, although it is so complicated, and we as humans had studied ourselves for so many, you know, several hundred years in brain science and neuroscience, but we still have no very clear picture about how the brain works. So this is a relatively recent studies in my life. And we say, although the brain is complicated, actually, the structures may be divided into different kind of memory structures. So I would say that actually this is our long-term memory. This is our short-term memory. And here is our visual memory. And here is IO, that's action memory, behavior memory. So we call the abstract behavior memory is in this part. And the short-term memory is in the frontier. And in the kernel, inside, actually is long-term memory. And this part is our visual memory. That's a part of our long-term memory, but there are short-term memories for vision information as well. And something was amazing in brain science actually is this area. This area is so important. That's called actually this is our conscious memory, conscious status memory. Well, our consciousness or our modeling about the real world situation actually stood here. It's not stood here, partially stood here, but the major map of our understanding about the real world situation is stored here, because here we have the whole set of memories, a whole set of sensories about all our body, of our brain, of our eyes, all the parts is modeled here. So here is just IO, it is a temporal situation. Here is the current status. And by compare those two parts, we actually understand what is changing, what is happening, what is the event we can capture here, and that represent in this area. This is an important part. It was not very well studied. So nowadays we really understand that this part is more important than other parts, because that's all those parts is only for memory or for information storage and holding. But these parts actually represent what is the external world for people. And look at the functional side. The function side is built on the structure side, but the function is different from structures. So you'll see human intelligence, actually, this is in one of the paper in attribute transactions. We see there are 7 layers of human functions. So the bottom 4 layers is called the unconscious or subconscious functions. So from the bottom is sensory, memory, perception, and action. So this is the bottom level basic functions. But as human, beyond animals, we developed the higher 3 layers. So from the metacognitive functions to meta-inference functions to the higher level cognitive functions. So this is our reasoning part. This is our fundamental part linked to the external world. And so the third three layers we call the conscious level functions. For in a words analog to the understanding in computer science, we would say this part is something I call it a human operating system, HOS, human operating system. This is the fundamental layer of human body or human brain's power. But this part is our apps, the human apps. So all the things as individual behavior, or you learn something, or you're doing something, that is implemented by these three layers. Anything beyond is your everyday life, everyday behavior. So this is, so you say eventually the function of human brain based on these kind of neural structures becomes a kind of human computing system with a human operating system and a set of pre-trained or experienced behaviors. And you use this part to deal with external situations all the time. So this is a whole picture about brain science and the relations with computer science. So this is what we call the brain-inspired systems based on that fundamental structures. So this is my experience. I was visiting a number of these top 10 universities. Actually, that helped me, give me a chance to interact with all the pioneer scientists in these universities. I learned a lot. That led me to develop some of the theories that's cross boundaries, cross disciplines, that help us understand what is natural intelligence, what is the potential solutions towards the future of development in our field. So then before we discuss any further about detailed theories, we need to understand what is the constraints of current AI technologies and theories. So that means now the constraints is focused on what can the AI do for us. And just by understanding that, we know what is the constraints of our current theories and current technologies. And we will understand more about the future development, well, what is the future directions we may reach, what we are going to do. So then you say, in this part, we are going to discuss first is human intelligence. Actually, intelligence is not built, intelligence is not directly generated immediately in the on the neural structures. There, you see the cognitive entities in our brain have 4 layers. So the bottom is data, then information knowledge, to intelligence. And also the understanding is we can cross this. You see, we can jump, say we got some data, we are going to generate some intelligence. There is no way to do this. And we have to do it layer by layer. The data will be transferred into information and then transferred into knowledge. Knowledge will help us to generate wisdom, we call it intelligence. And if human can do this directly from data to intelligence, and if we believe a machine can do it, by neural network, we can say if people assume if you collect enough data and you can generate better intelligence, sometimes you believe that could be advanced than human ourselves. Actually, we would say there is no such way. For example, this is a fundamental challenge to train our neural networks to understand the big data. Say we have an AND gate. The AND gate, say if you have an AND gate, that there are 10,000 pins. So then you see at the data level, what is the space there? It is too big. It is 2 to the power of 10,000 bits. What this means? This means if you hear all the people in the world working on this and counting on this, you need millions of years to finish it. So you say, if you work on the function, it is diverse. The output is diverse. You never work on the output side of it. Otherwise, it is so large and that's meaningless. But you have to get back to the input light. So this is why we say we can reduce this kind of problem that's so big and so complicated. But we can reduce it into information. Eventually we say, okay, the bit of information is only 10,000. It's much, much smaller. We reduce it immediately to a smaller size. And then what is things onto the knowledge level, we say, we immediately reduce the 10,000 base to 2 basic rules. What is the rules? That means if all the input is 1, we got 1 as output. Otherwise, we got 0. And you see, this is human power. We gradually and fast reduce a very big, almost infinite space to some things inductively as rules. And eventually, when we reach the top level intelligence, we say this problem actually have no relation with the number of pins, how many pins there, because for any given pin, the output is just the function. We call it AND function, relate to n, whatever is n, if n is greater than 2 or greater than 1. So this human power, you see, we reduce so large, almost infinitive space to the intelligence level or aggregate from low level to the higher level. The machine learning result is, okay, that's only an AND function, even with no relation to how many pins there. Whatever is number of pins, we have the same function. So this is human power, but but how you train the machines to understand this? Never, you can't, because if you train the machines from the first combination is 2 to the power of 0, and then to 1, and then to 9,099. You see, after you're training all the 99% of the things, the machine says the output is 0. And only if the training is reached the last moment, there is 1 happening. So if you use neural net to train this kind of magnets, the machine says, what is AND gate? They understand AND gate is a dummy device. That is, whatever is the input, output is 0, because you may not reach the last moment. That's the situation. So this is the differences between machine understanding and human inductive reasoning. Okay, there are so large gaps. Our machines at this moment, based on the neural network system, it doesn't work there. And also, let's look at another thing about the absolute intelligence. We say absolute intelligence, as in our brain, have 3 levels. There are different things. Their properties are totally different. So with current AI technologies believes data determines everything. Or if we obtain enough data, we can obtain higher level of intelligence, even super than human brains. Actually, there is no hope if we believe in that way, because the four of the things their property are totally different. And if you look at the units, you would understand they are different things. For example, data is based on qualification system. So the unit is just a unit of how many bits. The how many units of your measurement skill. And information become a bits because Shannon already told us. But what is the unit of knowledge? And most of people in AI would say, okay, knowledge is still counts by bits. Actually, it was not. And you say the definition of knowledge says that's a Cartesian product of information and concept. We map this space to knowledge. That means if we have a piece of information, we have existing concept or new concept. The combination of them builds our knowledge. So eventually you see this clearly. This is a relationship. So this is my discovery in 2018. We say the basic unit of knowledge actually is a beer, is a binary relation. So it is much complicated than bits, binary digits. So Shannon told us about information, but actually this is the latest discovery about what is the nature of knowledge. And then intelligence. What is the nature, basic measurement unit, based on this definition, that's a Cartesian product between informational events and another dimension. It is the functions you already built. So this kind of functions you built is somewhere these layers. Okay, that's the functions you built. And the information or stimuli with a Cartesian product of your pre-built functions that becomes behavior, becomes intelligence. And also interesting is the unit. The unit of intelligence actually is a BIP, it's a binary process. That means any process you build, and if that's a hook to the external information or events, it becomes a piece of intelligence. And you see all the things here tells us the entities we are dealing with in the brain have totally different mechanisms, different mathematical models, or their properties are totally different. We can't believe you can jump from data to intelligence without the aggregation level by level, eventually you can reach here. So there is no way for jumping. And so this is, let me give you a couple of examples. So for example, if you're just doing, the first example is the AND gate we already explained. So here is another example says, if you're just doing data aggregation based intelligent generation, you would get a number of conclusions that would be confusing. Would be seems your reasoning process was right, but your conclusion would be that's a humor. For example, you say based on big data, we observed the suns rising every morning after the singing of the roosters. If the roosters is wake up and singing, and then you would expect the sun is rising. The data, big data, if you use a neural network training all the big data, they say, okay, the Earth working this way. But actually, of course, we see this is not true, because if you remove all the roosters from the world, the sun will still rising. So that means this relationship neural network would observe based on big data would not be a causal relation. And they just find something, it appears have a relation, but not necessarily and not sufficient. So that's another situations based on neural network training. And you observe that people get old on the Earth or other planet because our Earth is rotating clockwise. And then you would suggest, okay, we actually may get younger every day if we move to another planet that's rotated in anti-clockwise. And actually, we haven't proved if this is wrong or not. But actually, the data just tell you in that way. But we need experiment, we need observations. Perhaps it happens, or perhaps it's not a causal relationship. So all the things is just based on neural network training, actually we can get real-level knowledge and real-level and dependable intelligence. So we need, study the mechanism further and understanding the causality between the things. So that leads to the studies. Okay. So the second discovery is the actual intelligence is embodied by causal inferences. It's not just based on data received. Data don't reveal or contain the internal essence of causal relationship. We still have to understand that the alpha I or any kind of intelligence is a kind of behavior based on the event information to behavior to knowledge. They are not directly based on data. What data is the materials or raw materials of information. Okay, So this is all the relation we discussed. Another thing more important is our reasoning is a causal system. So as a causal system, we say any piece of intelligence is a necessary sufficient causality rather than one directional driving. Because this kind of data and the average or maximum tell us something. It is not reliable. It is not causal. So that means in our reasoning system, you need to do two things at the same time for any reasoning. One is to find the changing variables or changing concept events to find the sufficient condition. That means something happened based on essentially based on something, and then another part should be established as well. Is called necessary. If something happen, always trigger something. We need the analysis of necessary. And if the necessary conditions is not there, it is still not a piece of basic understanding about the causality. Just like the previous examples, you see, we observe something there is a necessary relationship, but one of the relationship, but they are not sufficient. So that's where the reasoning could be wrong. So the machine intelligence nowadays is still at this level. They get some conclusions, but many of them are not reliable or trustable. And based on that, we say our future to improve the AI technology and our reasoning power to move the AI series to closer to the brain, to human power, actually to improve all the things here. As we say, we need imply both causal relationship in machine level reasoning. And also in the future, more important than reasoning is another thing called intelligent generation. That means that by observing all the data and all the learning process, we want the machine actually, eventually they should be able to generate their own intelligence. Rather than say, okay, they just know data and based on data, what is appearance? This is the current level. We want in the future, the machine, we would enable the machines to generate their own intelligence. It becomes a part of human intelligence because this is a human enabled. At this moment, we still didn't reach that aim. That's the ultimate aim of intelligence science, artificial intelligence, and computer science. And another one is to autonomously generate knowledge systems. The machine should be able to create their knowledge rather than they're waiting for us, for human to tell them. Okay, so both of them are parallel. You say if the machine have enough intelligent generation power, the sign is they can generate their own knowledge. If they may generate their own knowledge, they have a more powerful learning capability. So this is a sign in the future if the machine can learn knowledge rather than learn from data. Okay, so all this should be considered that the future of challenges for reaching the ultimate aims in intelligence science and machine learning. And so that will lead to something actually so we call the symbiotic and collective system of intelligence. So in this kind of symbiotic system, there is no difference between machine and human. So the nature, intelligence, and the artificial.
Tiene que ponerle que en la computadora.
But then, what you said? Okay, anyway. So this is the future. So eventually, if the machine intelligence is getting powerful, there will be no differences between machine and human. Then the symbiotic part is to integrate coherently into a kind of collective intelligence. There is no differences between machine and human. That's the future. So let's look at how we do this based on understanding about the current constraints of AI, how we develop this future symbiotic and collective intelligence systems between machines and humans. So that lead to the basic studies of intelligence science and generally. That means what is the generical theory and foundations towards machine implementation of AI. And so look at, so this is the first is concept of intelligence science actually is talking about theoretical parts of the mathematical means towards the dealing with abstract intelligence, whatever it is from human or from machines, from animals. And we're trying to deal with it as generical theory called abstract intelligence that would be implemented in different ways. And that would be different paradigms. But whatever it is, they share the same foundation or can represent the same way of mathematics. And so then this says we are actually our aim is moving the machine intelligence from bottom up. So we say we spend so many years, we're still here. We have to break the cap and then reach the autonomous company intelligence. So for each of the levels, I have detailed descriptions. We have no time to explain the details, but you see the base structure, the intelligence is represented by a kind of dispatching function with recursive structures. So that means there are a number of things that depend on external events or stimuli. Based on different stimuli, the system or the brain or the machine system will dispatch a suitable and proper behavior to deal with it at different levels. And once it reaches the top levels, there will be more clever behaviors, such knowledge generation and learning by themselves, and inference or reasoning by themselves, and generate inductive series. Once they observe enough side of things, they say, okay, there is a generical theory. Inductively, they tell us, okay, there is a rule about the things we are observing there. This is the level the machine really becomes something closer to human capability. And so eventually, so the understanding about the alpha-I, the basic intelligence series is the intelligence is actually a recursive system from the bottom up. That means once we know the layer k-1, we can build a layer k. And or inversely, we can reduce higher layers to lower layers by this kind of recursive system. And eventually, each layer, the bottom layer is data, and data is represented if we know the set of data, and then information will be generated, knowledge may be generated, and then intelligence will be reached. So there's a basic understanding about how the brain works in a rigorous structure. So based on that, so we're going to, one of discoveries is, okay, actually the objects in both intelligence and AI shares that shares something that actually hide already out of our domain of understanding. Or you see our number system will stop here, real numbers for almost 200 years from Descartes' work in France. Yeah, but now we reached here based on Professor Loftside's discoveries. There are foreign numbers, actually it's two-dimensional structures with a value and confidence level. And now we extend this to n levels, n dimensions, like these structures. So we call the hyperstructures. That means not necessarily 2 dimensions or 1 dimension. There could be infinity or multi-dimensions. We call it, this formula, we call it tuple, n-tuple. That means there are n individual dimensions with constraints. And you can extend it into detailed structure like many lines in n-tuple. So this is what we define H. We say intelligent science and machine learning, all the intelligent system eventually is working in that extended scope, not in pure numbers. That's why only based on data training, you are not necessarily generate good machine intelligence. So all the things then eventually focus on RFI, is how the machine may generate these kind of things like human. And so then for the current domain of our representative power had out of the things we know in nature numbers, real numbers, what should we do? And this is the whole picture says, okay, actually as human, our everyday life is dealing with to be and to do problems. And whatever they are majorly in to be and to do domain or category. There are small categories to have that could be sometimes closer to be, sometimes closer to do. Well, that's an extension of to be. Okay, we only deal with two of these categories. So then what is the mathematical model that support us to do this? We say conventionally in our existing methodologies, we use logic to deal with to be. We use functions, calculus to deal with to do, but they are inadequate. They are not enough because the things and the types, they are sometimes too complicated that out of our capability or means. And then this latest development in the last 2 decades in my lab, actually we developed a lot of things called, in a family, we call it intelligent mathematics. So you see, for dealing with to be, we develop something called concept algebra. That means how you build up your basic unit of knowledge. That's called the basic unit is concept. Then semantic algebra. What is the meaning of each of the concepts and their mathematical operations? Fuzzy logic, everybody knows this, and big data algebra is how the data may manipulate in very large scopes that will generate concept, semantic generate knowledge. And there are visual semantic algebra as parallel of the semantic algebra. And then for the to-do part of the major structure in intelligent mathematics, we call it the behavior process algebra. That means how human or machine behaviors or process may be modeled and operated as an algebraic system. Just powered by this, our machines could generate future intelligence by their own reasoning system. So this is this also covers all the software science studies about how computers may generate programs for the AI system. And there are inference algebra that's more important, to do induction and deduction in a system that help us reasoning in a rigorous way. And also there are fuzzy structures corresponding to this. This is a picture to say what we did for the fundamental part of intelligent science based on underpinned by the mathematical models. And based on that, we say we actually, that help us to understand, okay, the new problems demand new forms of mathematics because the domain of our target in intelligent science AI had already out of the domain of our real numbers. We have extended it to more complicated hyperstructures, and then that we can build an algebraic system to deal with that. That becomes more powerful mathematical models. So the reason here is highlight here says, okay, we are in AI and the intelligent science. We're dealing so many things that they are no longer a pure number. You'll say, what is a concept? What is a system? And you can't simply say, use the nature number to denote it. And each of them are out of our capability or our domain of modeling. So that's why they are hyperstructured rather than pure numbers. And then, so this drive us to develop so many whole bunch of algebraic systems to manipulate each of them in a rigorous way. So that becomes a power to deal with all the things we're expecting AI, intelligence, knowledge, and systems using cognitive functions about brain. And this the picture says what we need in a discovery in an extended field of AI and brain-inspired systems. So that leads to the current direction says we're developing autonomous system AI, we call it double AI. So this is the AI should not be data-driven or should not be pre-trained. That should be autonomous. That means they work by themselves to generate something for our needs rather than we train them. Because the training-based ideas is not a great idea. For example, for the very well best trained neural networks, say from Google, from Microsoft, to recognize human facial information. And if you have a group photo, a family photo, if you feed in your photo in an upside down way, and what is the best neural network will understand, they will tell you there is no person, no facial information, because they never trained to understand the upside down information. And also we test in our project, we tested another situation. If you feed in a photo with somebody, their eyes were closed. So that means when you take the shot, somebody was not open their eyes fully. So in that situation, what would happen? And the best trained neural network, actually, they say, okay, there was somebody there in a photo group photo, but somebody is not a human, or there is no facial recognition for that kind of people because their position is normal, or their eyes are closed, or their partial mask by some part of their clothes. So this is actually says our current data-based or training-based technology or not a final solution or powerful solution for AI system. We have to enable AI to autonomously figure out the things rather than just based on training. And another situation is why we say this is not a generic solution as our current technology of AI, because in many of the real-time systems, there is no opportunity to allow you to pre-train your system. For example, you are driving, you control an airplane, or you control a missile. You have no time to say, okay, let's retrain my system because situation changed. There is no way to do that. That's why the final destination or ultimate aim of AI actually is autonomy. So we call it AI. So what is AI? Actually, is still brain inspired. So this is the details of our brain models. There are 7 layers as we explained. The bottom 4 layers are our human operating system, and the top 3 layers are apps. And then anything beyond age is derived, autonomously derived in our everyday life. You don't ask anybody, say, can you train me again because I have a problem. And actually, all the solutions is derived based on all the things had already built in our brain, particularly learning, the autonomous learning system, autonomous problem-solving system, autonomous decision-making system. So all the things actually, so all the future autonomous AI is still built this framework, no differences. And so all this framework will lead to one of our partial implementation called the cognitive robots. So these robots will built in with this kind of human-like or brain-spirit framework to implement the future of next generation of AI technologies. Another discoveries in these studies actually says how much we can learn. And if we are going to train on a machine, if we're going to build very advanced knowledge, is how much we can learn, we can memory in our neural system. Which the fundamental mechanisms is well known. Okay, so we say that our knowledge is represented by the synaptic connections between the neurons. So we are not to put our knowledge or information in a nucleus of the cell, rather than we use synaptic connections to represent the knowledge we learned in the brain. The machine should do similar things. Currently, the machine uses the cells, use their memory cells to store knowledge. It is compared with the power of the knowledge. It looks a little bit stupid. Okay, So then this is a challenge in neuroscience and brain science, also computer science, is what is human capability of memory? How much we can learn and we can remember. It was a challenge. Actually, there are different ideas, and in most of the times there is no idea. Based on this generic observation about synaptic connection, we say the things you can memory becomes a combination. That means N is the base of how many neurons there in your brain. M is how many connections in between a pair of brain you can generate, you can grow, and that becomes your memory space. So, but eventually, once we got these models, we tried to solve it, but there was a difficulty challenges because the things here are too large. Because this is N here is 100 billion, and N here is 100 billion, and the connection M here in average is 1,000. And then, so no computer can solve the problem like this in combination. So then eventually we found an algorithm to reduce this huge size of combination into the approximate solutions. So eventually we got results. And this is results of the solution to see how much the ordinary human brain can remember. And this is our representative space in the brain. It is a 10 raised to the power of 8,000, more than 8,000. How much is this? This is much greater than the chips and hard disks of computers. If you collect them all in the world together, there is still a small piece of this. And that's the situation. So there is a story in 2003. In southern France, we had a conference. There were two keynote speakers. One is the chief engineer from IBM France, and the other one is me. But somehow my talk was in the first day to talk about these findings. And then the second day, the chief engineer of IBM France, and when we meet in breakfast, in breakfast, he told us, I could not sleep. I say, what happened? He said, I had to change my slides last night. I asked why. He told, you present something like that. But actually, in his previous slides, he prepared. He would claim in the next 10 years, the chip's capacity of IBM will be greater than human memory. And once he see this conclusion, he gave up. And he would never say any human-made chips would be greater than this. There is no way to do that. That's why after this, you said nowadays 20 years had already been passed. And actually nowadays, no company would say this kind of hypothesis. They will build brain-like chips that's greater than a nature brain. Actually, nobody can do this. So this is the power of theory, power of math that explains a lot of things. Another discovery is about human learning system. You see, we were focused on very simple learning, pattern recognition. And actually something missing is the last two. This is my theory. This is how the machine would learn knowledge rather than object orientation, object identification patterns. And also another thing more important is intelligent generation. So that's based on this. What is machine intelligence? What is the basic function of intelligence? How the machine would generate that? So all these two kind of things, if we can get some breakthroughs, you would expect very powerful AI machines in the future. But now we still have theoretical, challenges. We have technical challenges as well. But the major thing is a theoretical challenge. We don't understand what is knowledge generation by computers. We also don't know how the knowledge will become behaviors. That's intelligent generation. And so I would predict in the future, we are going to actually address those two challenges. if we can't make any breakthrough there, the AI in the next couple of decades is still the same. And although there are fancy applications, they didn't solve the major problems towards brain-inspired functions, or what is it, the nature intelligence do there. Okay, so this is a basic understanding. Okay, I will skip some of the things, and we say enable machine to learn human knowledge is because that's you need to understand what is knowledge. The knowledge is a function defined here that transforms information or data into concept. So this is a single piece of knowledge. And then what is the whole space of knowledge in a human brain or in a future machine? It is a set of concepts mapped to another set that becomes our whole knowledge. But this is still not the end because the entire knowledge becomes a hierarchical structure. That means you have all this key, it is all the relationship mapping between all the concepts. But there are layers. Some layers concept will generate a higher layer. This layer will generate another layer. They're embedded together, you see. This is the bottom layer, you have individual concept. This is another layer, you would have group of concepts. This is a discipline of concept. This is a whole knowledge in a person or in a computer's memory space. So this is our mathematical model of knowledge. If it is also within knowledge, base unit is a beer. It is all these kind of relations. And then you see this is a simulation. Our machines within seconds can build up our ontology or basic knowledge. This is the first 600 concepts in English. Most frequently used words concept in English. And if we ask human do this, because all the links are quantitative, the machine analyzes what is the level of their relations. And if human do this just for 600 simple English words, they can build a knowledge network like this because they would need several years. Or if you hear a group of researchers, you still need, say, several months to deal with just the 600 generic English terms. But the machine can generate it just within 2 seconds. So that means this is machine power. Eventually, they understand the human knowledge or the basic unit of human knowledge is all the concept very accurately than human ourselves, even than the designer of all the dictionaries, the expert of linguistics for their, this is our simulation. That's the things we already reached by machine learning for knowledge, not only machine learning for image recognition, that kind of simple things. And so that leads to the implementation for the future of robotics. Okay, I think this is already the time, and so before the end, it says, so this is to say, once we are doing basic research and mathematical-oriented basic studies, actually that lead you to a better understanding about truth, about the essence of the field of our doing. So then you see this is my input in this Google Scholar recognized in cognitive robots are #1 in the world based on publication index. In software science, I'm #1. And I'm #2 in cognitive computing and #8 in autonomous systems. Okay. And that's not a coincidence. And based on ResearchGate, and they recognize me in general as #1%. That means, and indeed in specific disciplines here, and I was #1 recognized. So this is not a coincidence. It is based on all basic research and also there's transdisciplinary research. So this is my current record. You say, formally proved the Goldbach conjecture, this. And that's had already published in Weiser Transactions of Math. And also last 2 weeks ago, words in Athens in Greek to report both of the results that had already been published. And it is two keynotes in a mass conference, European mass conference, talking about both of my proof of Goldbach twin prime conjectures. So you see, this is not easy because the Goldbach is 180 years problem. And the other one is 170 years or something like that. But now we got a formal proof. And also that's not a very difficult, not a very complicated one because all the simulations, they're based on mathematical proofs there. And there are different ways to prove the same things. And actually that enabled me to prove something more in the future. Because you see, the transdisciplinary studies and fundamental research actually extend your mental power to deal with more complicated things. Or in other words, those kind of things, people in pure minds would found it is so hard. But now for me, I don't feel that those kind of things are that hard. Because in artificial intelligence, in all the intelligent, intergeneration and brain space system, their difficulty and challenge are more hard than this kind of pure math problems. That's my feeling. And we are going to, organize the 21st HB conference on cognitive informatics, cognitive computing. So it is planned in December, in middle of December. So the deadline, there's still a few weeks of deadline. If our audience here is exactly the similar series of conference, and if you like, you would submit your papers there. Okay, so we hope to see some of you there as well. Okay, so any questions, please? Do you have any questions?
Does someone have a question?
Okay, please.
I have a question.
Okay.
Hello, Professor. I was wondering that maybe these intelligent machines of the future, they will have in some sense to rediscover mathematics, in the sense that these machines will have to learn how to count, they will learn how to represent numbers, they will need to create all the history of mathematics that we humans had to discover, that this system might have to discover by themselves. What is your opinion about that conjecture?
Yes, I would say you're right. Actually, we are doing AI, but most of us treat AI as empirical or technical study. Actually, it is not enough because all the rules, all the causality we understand as our basic knowledge is represented in mathematics. Without the math, all the other things we reach so far cannot be rigorously described. And then we can do rigorous reasoning. The machine is the same. If they don't understand your things in a mathematical system, they can't deal with it. But somehow in AI, this emerging field, we have no matured or ready mathematics, because even all the things we're dealing with out of our domain of representation rather than say reasoning. That's the bottleneck, and that's the constraints or challenges here. If we can't solve this kind of problems, and in the next 20, 50 years, we're still the same, our technology. Because, so this is reasoning about how the science was developed. It's not necessary for AI. And so I believe that's the only way to advance our field. If we don't focus on our mathematical means or our theoretical foundations, we really can't solve all the challenges. And that's the fundamental understanding. And there is no exception. Any disciplinary field developed in this way. Initially, there are some technical problems, and then in general, we found that are theoretical problems. And then we found underneath is a mathematical probe without a powerful math, and actually we can't deal with that kind of things. For example, if we never understand what is the mathematical model of intelligence, how you claim you can develop good intelligent system, you know, the causalities, there is no link in that kind of causality. So this is why we say brain spirit system eventually this is how you formally model the brain and model the behaviors, model the intelligence knowledge in the brain. And then the machine will be able to implement it once the theory is ready, once the mathematical means are mature. That's my perspective. That's the basic things. And we can't just say, okay, everybody, 1,000 people training neural networks. And what we reached is the best advanced branch in our AI is image recognition. Even for that, we still have no theory. Okay, we're just training different kind of neural networks. And you know, the direction is not that smart. And that's why thousands of our PhD students enter this field, repeatedly doing different trained neural networks. It is worries me, actually. Actually, we didn't have very important breakthroughs in this field. And of course, for the people from outside, from industry, they would say, okay, that's fancy and nowadays everything may be treated by AI system. Actually, we're still constrained by theory and mathematical means. That's my understanding. Well, from my perspective, I think in a way. Okay, thank you. Another question?
Do you have another question?
Okay.
No more question? Okay. Thank you so much, Professor Wang, for your talk.
Thank you. Have a good day.
We will continue with the next talk. Is there Andries Van here?
Hi, good afternoon. Tuning in from the Netherlands, Professor Wang, thank you so much for the interesting presentation. Can I just share my screen and take it away?
Yes, I see your screen.
Yes, if you give me 1 second, I will share my screen.
Okay, the next talk is entitled Modeling the Effect of Propanol Administration After Fear Memories Reactivation by a Second-Order Adaptive Neural Model.
Yes, thank you so much. So yeah, I'm Andries van der Meer. I'm a recent master graduate from the Free University of Amsterdam as part of the course Behavior Dynamics in Social Networks. We created a second-order adaptive model for fear extinction by administering Propanol law. Now, I might have a quite uncommon way of introducing the topic by means of a series of clips, and I want to give some viewer discretion. If you're afraid of spiders, I would not recommend you to watch these clips. But yeah, let's take it away. Can everyone hear the videos, by the way? So as we can see, he is very afraid of the spider. And then this is followed by the administration also, or by administering Propanol law. Then the day afterwards, he comes back and the following thing happens. incredible. He can touch the tarantula like he has never been afraid of it. Well, first of all, let's move a step back and introduce two essential concepts: the concept of fear and the dysregulation of fear. So fear is essentially of activating the fight or flight response to dangerous threats to prevent harmful situations, but it can be dysregulated, and that leads to an unregulated fear response. It can be induced when there is no harmful threat, and that leads to social anxiety disorders. One commonly known disorder is post-traumatic stress disorder. And a way to eliminate fear, a common method used is fear extinction learning. That involves the repeated exposure to a cue to produce the extinction of fear. And the neurological basis behind it is that we have the amygdala, the ventral medial prefrontal cortex, and the hippocampus, where the amygdala is involved in fear conditioning by a conditioned stimulus, which leads to a conditioned fear response. Then a ventral medial prefrontal cortex is mostly involved with retention and retrieval of memories. And the hippocampus is involved in the recall of extinction learning, but also the context-dependent renewal of extinguished fear. Now, what role does propranolol have to play in this? That is that normally norepinephrine enhances the contextual fear memory consolidation, and we can reduce the amount of norepinephrine by blocking beta adrenoreceptors with propranolol. So first, in this treatment, the fearful memory is recalled. Recall the person that went to the tarantula and got completely freaked out. Then propranolol is administered to the patient, which blocks the beta adrenoreceptors and decreases norepinephrine. And that leads to the reconsolidation of the fear memory and to fear extinction. So let's move on to the model. So we created a second order adaptive model, which includes a base layer where we modeled the presence of fear in each brain area, and also the propranolol and norepinephrine, which will be represented in states in this model. And in this model, propranolol reduces norepinephrine. Now, the first and second order layer consist of a layer that facilitates learning, the first layer, and the second layer activates learning. So our model consists of a total of 14 states, and we will walk through them right now. So moving on to the base layer, here we can see the conditioned stimulus that is picked up by the amygdala, which leads to a conditioned response. And here we have the hippocampus and the ventral medial prefrontal cortex forming the fear extinction model. And then the second base layer is the model where propranolol is administered to reduce the amount of norepinephrine. Then the first order layer contains 3 W states, order wave states, that have the Hebbian learning combination function. And that is to facilitate learning and change the hippocampal and the ventral medial prefrontal cortex state. Now, the second order layer activates learning. So recall that the first layer makes the learning or is responsible for learning, whereas the second layer activates the learning. And so looking at the role matrix, we can see here that the second order layer is affected by the norepinephrine state, state 8, and that the first order layer is in turn activated by the second order layer, and that leads to the affection of the hippocampal and the ventral medial prefrontal cortex state. And the weight matrix, which influences the learning of the hippocampus and the prefrontal cortex, is affected by the first order layer, like I just said. And as we recall it, that the first order layer has Hebbian learning. Now, moving on to the first scenario, here we can see that there is fear extinction with propranolol. Now, the base layer, where we can see the fear response, which is the conditioned fear response X5, you can see here clearly that it goes up, and then we administer propranolol here, which leads to reduction in norepinephrine. And then we can see an increase in the learning activity of the hippocampus, as well as the ventral medial prefrontal cortex. And that in turn leads to a reduction in the fear response. Now, what would happen if you would not administer propranolol? So in this scenario, we have we deactivated the propranolol state. And as you can see here, we have the same spike in fear and the retention of the fear response. And there's no learning at the hippocampus, as well as the ventral medial prefrontal cortex. So to move on to what this means is that these first scenario shows that propranolol is responsible for the reconsolidation of the hippocampal and the ventral medial prefrontal cortex state, and that results in a decrease in the conditioned fear response. Whereas if you do not administer propranolol, there is no reconsolidation and thus no decrease in conditioned fear response. So in this model, we can conclude that propranolol indeed has an effect on regulating the conditioned fear response by suppressing it with the new obtained memory through therapy. Now, the limitations of this model is that it is a relatively simplified representation of fear extinction learning and the administering propranolol. For example, you could also include the beta adrenoreceptors, and also the time frame is it really suitable, as in there's no empirical data implemented in a model with regard to the time frame. But nevertheless, the model does depict the process and impact of propranolol therapy over time, and it can be built upon. So I'm now just wondering whether there are any questions about the presentation.
Okay, thank you. Does someone have a question?
I'm also happy to answer any clarifying questions about the model.
Okay, is no question. Okay. Thank you so much, Andres, for your talk.
Yeah, you're welcome. Cool. Shall I just end my screen sharing?
Okay, we will proceed with the next talk, titled Cognidron AAG, a system based on brain-computer interface and a drone for cognitive training. It will be presented by Monica. Creo que trae su computadora.
which is a system based on a brain-computer interface and a drone for cognitive training. So first of all, here's an overview of what I'll be presenting to you today. So I'm going to give a brief introduction on the system and on why it was considered important and relevant to develop. Next, I'm going to talk about the system itself, its objectives, and its general design. Moving forward, I'll talk about the materials and methods that we use to design, develop, and test the system, including the participants, equipment, and scale that we measure. I'm also including the results of this evaluation for assessing the functional suitability and usability of the system. Next, the discussion that took place afterwards. And lastly, I'll be talking about the next steps now that we have this base on the system that we'll be implementing in the future. Also, I include the references of this presentation. So first of all, in the introduction of our article, we begin by describing mental health in general all over the world. And so we describe that mental health disorders can be divided in two categories. One of them is common mental health disorders, and the other is severe mental health disorders. And you might have heard of attention deficit hyperactivity disorder, or ADHD, which is considered to be the most common behavioral disorder in children. And an issue with this diagnosis is that it often lacks adequate treatment due to its symptoms. They can often be confused by other mental health disorders such as anxiety or even depression. And so this is why ADHD today can persist through adolescence and adulthood. Fortunately, there have been non-pharmacological approaches that have been developed recently and that uses technological implementations such as serious video games and robotics that have shown to improve behavioral self-regulation of the symptoms in children with ADHD. For example, on the left side of the screen, you can see the image of Focus Pocus, which is a cognitive training system that uses a headset, and it's also a brain-computer interface. And it includes both biofeedback and neurofeedback for cognitive training. So now talking about the system, Cognitron EEG is a game-like designed cognitive training system to reduce ADHD symptoms. I mentioned that it is a game-like design training system because we considered one of our hypotheses was that when it includes the features of a video game, it will increase the engagement of the patients to the treatment, and it will be fun for them to train, and it wouldn't feel like just therapy or a serious session with a mental health professional. And also, Cognitron EEG involves both a virtual and a real environment, and is designed to be developed using an incremental approach, meaning that this is only the first version of Cognitron that you will be seeing, and in the near future, it's expected to continue in development. In the left side of the screen, you can see Cognitron EEG's virtual environment, which includes a virtual drone and has features, as you can see, such as stars, which represents like the goals the patient must achieve in order to gain more points. And also on the right side, you can see Cognitron EEG's real environment, which includes the monitor available for the therapist that can see how the session is going. Here you can see the participant using the headset and the drone flying. As you can see, the drone is flying in a reachable distance from the participant on a safe distance, and it is very suitable for this kind of cognitive training. Now, regarding the objectives of the development of this system, we have that the first of them was to provide a set of cognitive training exercises that will improve cognitive attention function in healthy subjects, not only in mentally diagnosed children or adults. So this is an important feature because most of the cognitive training systems that are available in the market are only focused in diagnosed population. The second objective was to maximize the cognitive training's positive effects, meaning that the system by itself wouldn't substitute the whole therapy session. And there are also like another features that are needed to be included for the participant to have a complete or iterative development of his or her cognitive skills. On the general design of the system, by following the ISO or International Standard Organization guidelines, we identified the need for 51 functional requirements and 13 non-functional requirements that were going to be implemented in order for the system to function appropriately. In this image that, it's a little bit small, you can see that there are several subsystems that correlate to each other through interfaces. For example, there is the database module, the emergency landing module, also all the managing of information modules. For example, the data of the patients, of the therapists, of the tutors, of the children, and all of them function together to create what is the PCI as a whole. And for example, you can see from here the beginning, it all starts with the headset, and we could say that it finishes with the drone movement. Okay, so another important feature of the Cognitron EEG system was that it is based in the concept of feedback. And there are 4 types of feedback that were implemented in this system. The first one of them is the drone feedback, which is, by the way, the drone that we implemented was the DJI Velodrone. Also the sound and speech feedback, which provided motivational quotes to the patients in order for them to understand and to be able to know how their performance is currently being, monitored. For example, when the patient took too much time in achieve the goal set by the therapist, about 30 seconds, then the system will play a motivational quote such as "keep going" or "you can do better" or stuff like that. And whenever the patient, on the other hand, would achieve the goal in the expected time, it will congratulate the patient. So this is another feature that is like a game, so that they earn more points and they keep motivated intrinsically, not only externally by the therapist. Also, another feedback type that we used was neurofeedback, provided by the Emotive Epoch headset, and which is composed by 14 electrodes. And lastly, the therapist feedback. It's important to mention that the system by itself could not replace the therapist intervention, because it's the therapist himself or herself who can provide the patient with relevant information on their session. For example, you did better in this, you could improve in this, so that they could understand what they did good in the session and implement it on their daily life, so that they can self-regulate their behaviors. Okay, so on the general design as well of the system, we have that this is the Cognitron EEG system user graphic interface. So first of all, sensors will be selected by the therapist, and the therapist could know the signal quality based on the colors provided by the interface. For example, green meaning a good quality signal, yellow a medium quality signal, red a bad one, and gray non-existent connection. Next on this bar on the right side, you can see that there is also a green bottom and the red bar. And so the red bar represents the goal set by the therapist. For example, this can be manually set and also automatically set by the system. And so this represents the brain activity of the patient and the signals that are being transmitted from the headset to the software. And as I said, whenever the patient will achieve the red bar, a sound will be played in order for them to understand that they are doing good. And lastly, as I mentioned before, it will all end with the drone's movement. At the moment, there are 9 predefined flying routines provided by the system from which the therapist can choose from. And so whenever the patient will achieve the goal, one of the movements will be played. For example, to elevate, to land, to turn around 90 degrees, for example, to the left, to the right. And this would also be fun to the children to see. Okay, so now I'm going to talk about the evaluation of the quality of the system. So we conducted a controlled trial with 3 purposes. The first of them was to evaluate the functional suitability of the Cognidron EEG system. The second one was to identify mood changes in the participants after using it, the system. Next, we will compare the user's preferences between the Cognidron EEG and a commercial BCI that was selected to be the Nexus system. And so this evaluation consisted in 2 stages. The first one of them was to gather a group of children whose parents would agree or consent for them to participate in this study. And when we gathered their consent, we would apply some psychological assessments. The first one of them was the Shipley test, which measures intelligence, and the second one will be the neuropsy, which measures attention and memory. And so this will give us the reference to be sure that the children will be able to not only understand the instructions, but also to attend it. On the equipment that we used, as I mentioned, we used both the Nexus system, which you can see in this picture on the left, and on the right side, you'll be able to see Cognidron being used in a training cognitive session live. So for example, on the left side, you can see the Nexus hardware. You can see right here, you can see the minicap that Nexus uses, the participants monitor. In this case, it was a virtual environment that it is space themed, such as a video game. And similarly, they have a bar, a threshold bar, from which the participant and the therapist can see the performance of the patient. And on the right side, you can see the picture of Cognidron. And it's the same one as I mentioned earlier that was included. You can see the therapist monitor, the drone, the participants, and the headset. Okay, and so regarding the scale for measuring the system, we use some pictorial scales. The first one of them was the PICA mood assessment, which you can see in this picture. It includes 9 different moods from which the patient or the user can choose from, ranging from neutral to boredom to annoyance or excitement. And also, we use the self-assessment mannequin scale that you can see on the right side that measures the pleasure. It's not very clear from here, but you can see that it includes a different range of facial expressions from which the patient can choose from. And it measures pleasure, arousal, and dominance. And it is worth mentioning that these scales can be used for a variety of purposes, not only in this kind of assessments, technical assessments, but they measure the moods of people in a variety of scenarios. Also, we adapted the game experience questionnaire, or GEQ. We included 4 of them questions, which were originally about their team, to explore if they felt challenged, competent, or annoyed while using Cognitron EEG or the Nexus. And on the results, we could find that 100% of the functional requirements of the system were implemented. And 96% of them were correctly implemented and then corrected to achieve the 100%. The modules that had areas of opportunity were the managing of reports and also the control of the drone. But as I said, this was all corrected in order to achieve the 100%. Another result that we gathered was that 70% of the participants showed a preference towards the Cognitron EEG system over the Nexus, which confirms our hypothesis that the drone will be like an important feature, that a distinctive feature from Cognitron to other systems, so that it was more remarkable for the users to see a drone flying and to feel like they were controlling it with their minds. Finally, and this suggests that the Cognitron itself has a comparable quality regarding other commercial systems. The discussion that took place afterwards was that the drone, the DJI-Tello, was found to make participants feel safe. As I mentioned before, it flies on a reachable distance from the participant, and it can also be flied indoors, differently from other drones that only can be used on the outside and that can be very loud or can be very hard to manage. And on the other hand, this drone was found very effective and very easy to control because of its features. Another point worth mentioning is that a BCI like Cognitron EEG could help strengthen the subject's intrinsic motivation for doing this kind of cognitive training. As I mentioned before, this is related to the fact that it included game-like features. And so the mood induced by Cognitron EEG tended to fall within the range of major relaxation and major arousal or excitement. And this is a great result, meaning that it doesn't bother the users, it's not annoying, it won't frustrate them very much. So this is a good starting point. And also the non-statistical differences, as I mentioned before, prove that Cognitron's values are equivalent to other commercial systems, such as the Nexus that we used. The next steps on this development are, first of all, to work with a group of healthy children for a more extended, for an extended period to validate the system's efficiency. Because right now it was in a very short period of time, in about a few weeks, that we applied all the tests, all the cognitive training sessions, and gathered the results or the data. And the second next step will be to involve a group of children that have actually been diagnosed with ADHD to validate that the system effectively improves the mental health of people, and it's not only system effective. These are the references that I included in this presentation, and thank you very much. That is all on my side.
Thank you, Monique. Does someone have a question? Okay.
I was wondering, do you think that this same kind of control could be easily ported to different kinds of, let's say, games or the control of other kinds of autonomous vehicles or things like that? Or do you think it will be necessary to rethink everything again? how easily it is portable to other kinds of applications?
Okay, so I think there will be some features that will need to be adapted, but actually it's in the future planned to include a robot now, for example, which is another type of robots that have been used in this kind of sessions. And it could also mean that another vehicles, automated tools could be implemented. Yeah, I think that is very feasible for the cognitron to do.
Thank you.
Does someone in the audience have another question? Okay.
Maybe it's a very simple question, but in how many children was Cognitron was proven?
Yeah, thank you for asking. I skipped that part. We tested the system on 12 children, aged from 7 to 14-year-olds, both girls and boys.
Thank you.
Okay, I think I don't have more time for another question. We proceed with the next talk. Thank you, Monica.
Okay, some questions? Ricardo?
I was just giving the opportunity for others. But my question is, if I understood you correctly, even though you are making a simulation, you're making a simulation of real rats. Is that correct? Do you think that it would be possible to also have a rat simulation in the sense of you having a way of showing them moving around in a place such that it will be more easy for us that are not working with the neuroscience to realize what is the effect of all these triggers in the actual behavior of the rats, for example, running in a maze or something. Do you think it's possible to think about doing such kind of visualization?
Yes, because there is works from the lab in the Institute of Neuroscience showing activity, brain activity, electrical activity of the rats during that kind of stuff. So we have the data. What we don't have yet is the simulation of those data. We have only a very simplistic neural network because we didn't try to make a simulation by spiking of those those neurons, but we can do it, and that is a good future lead for the work. Thank you.
Okay, another question? No? Okay, thank you very much, Francisco, for this presentation. Who is the next? Dominique.
Hello. Dominique, unfortunately, last moment couldn't come. So on behalf of her, I'm going to present this paper today. That's okay?
It's okay.
Yeah, okay, perfect. So should I start my screen right now?
You can share your screen.
Okay, thank you. Perfect. In that case, I'll start right now. So first of all, thank you for giving me this opportunity. Today and good afternoon, I think it's afternoon there. First of all, our paper is the second order adaptive neural network model of dreaming and creativity, which I'll present today. And before I will introduce my topic based on an example, because you probably know the benzene structure thought by or made by Kekulé. He allegedly dreamt about this structure in a cabin. This dream can be considered a creative dream. Previous reports have also shown us that these types of creative dreams, so dreaming about something and then using that content to solve a problem, occur about 8% of the time, which is actually quite big. And even though the prevalence is relatively high, there is actually not that much research about this topic or phenomenon. So this is why we took it upon us to try and create a model about it. That was the introduction. Next, I'm going to talk about the mechanisms, our model that we designed, simulations, analysis I do not have in here, and the discussion. So first of all, we define dreaming as a series of activated mental images as internal or mental simulation with hyper-associative characteristics, such as you have different types of contents sparsed in your head that are non-obviously connected to each other, but this hyper-associative characteristic means that it could be connected to each other, even though it does not seem plausible. For example, relating an ape to iron. This can be seen as creative or associative thinking. Creativity is defined as the ability to combine associative elements, which means to create a new combination using previous experiences. So also a sense of our associative thinking. We found in our literature that there are similar brain and cognitive processes. The ones that we included in our model are that there's an increased striatal dopamine concentration, which facilitates cognitive flexibility and cognitive exploration, which is defined as associative thinking. And this concentration is actually increased in striatum during dreaming. Furthermore, the inhibition of frontal regions, in this case, we took the BFC, during wakefulness are actually preventing or repressing this associative thinking from happening during wake, but are less active, so allows for hypersociative thinking during dreaming. And as well, strengthening of learning happens through prior experiences. Yes, so with this basis, I will bring you through our modeling approach, which is a self-modeling approach made by Untitled, which models complex dynamic and adaptive processes, including single causal impacts, aggregation of multiple impacts, and also modeling the timing of these impacts to happen. So next, on the left or on my right, I have descriptive. I have my descriptive model, and the pink planes are the base layer, which is just a singular situation effects has, or an effect is happening, not really adaptive or dependent on anything else. The second layer, or the first layer of adaptivity, however, models this learning of types of connections that we make. It basically helps us sort of like based on Hebbian learning principle, neurons that fire together wire together, you're likelier to remember these types of, let's say, dreams, if you learn them, right? And the second order is the speed of learning, which is modeling metaplasticity, which controls whether learning will happen or not. And now I'll show you in an illustrative manner how our model looks. So this is our base plane, and as you can see already, there is a repetitive structure in the middle. These structures that are repeated are basically dream stages. As we know, our dreams consist of stages or a representation of something that's happening. I want to illustrate that these two PBs mean problem stages. So there's a problem in the wake that someone has, and during a dream, we'll get to some type of solution. Let's do that. So the first, I'll explain how this system works, because it is essentially a mental simulation of our dream. And you can see that there's a choice being made here. This is a mental simulation or mental image of our dream, which leads to a choice process. And reality is probably much, much more chaotic than this. For clarity, we made it more simple. We have, for example, we have a choice between eating ice cream or riding a horse. We assumed in our model that based on personal biases, we automatically choose one over the other. Therefore, in this model, we chose the images, or let's say states right now, to model the simulations. So what happens over here is that, okay, we chose this stage. For example, we choose to eat ice cream. There is a bidirectional arrow between these two choices because it's a winner takes all principle. Once eating ice cream, the idea of eating ice cream is more attractive. It activates more, therefore will probably simulate that mental image in our dream stage. Yes, so in this case, the result of this is eating ice cream. And that process continues on the multiple stages of our dreams. As you can see in the front here, this is the prefrontal cortex, or the frontal regions of our brain that we assumed based on the literature that kind of represses, represses the dream stages to allow for hypersociative thinking or an increased chance thereof. The WS state means waking, wake state, and the DA is the dopamine, and the SS is sleep stage. As you can see here, when we're asleep, it represses has a repressed effect on the frontal regions. but it has an increasing effect on dopamine, which I'll show in the next part, which is the first. If I can press next. Yes, the next part is the first order of adaptivity. It's not very well shown here, but there's an arrow going from dopamine to the TPS, which is an adaptation of the thresholds of the preparation states that you saw before. Also, these preparation states means the preparation for this imagery of eating ice cream, for example. This lowers the activation states, which means if there's a lower activation threshold, it means that there's a higher chance of this state or that PS state of eating ice cream increases, therefore you'll imagine that dream. And that's further repressed by the dopamine. And therefore it decreases all of these chosen states. The next one is based on Hebbian learning principle, the W states, which basically include learning, as well as remembering or retention of that learning of these states that we chose, one of which is the eating ice cream, once again. The last layer we have is the second order adaptation. We found in literature that actual dream recall is very much associated with remembering your dream. So this MW state means the retention of or remembering those dream stages that we talked about before, which relate to all the chosen stages we had. And the HW stages, again, represent whether there will be learning. So if they were not here, there probably wouldn't be any learning at all. This is the entire model. And as you can see, as I described before, there is a connection from the minuses over here, but this minus should be there from the dopamine to the thresholds or adaptation thresholds, which then lower all these chosen preparation states for the dream stages. Okay, so the first simulation that we did was with dream recall. To illustrate our model, I basically have these problem states. This is all during wake, all between here. And this is the sleep state. So a person occurs one problem, dreams at some point, and at another point in time, let's say 24 hours later, that they reoccur or the problem reoccurs. So they will have to think about the problem again. This shows the biological underpinnings that I spoke about before, which is the increase of dopamine in the striatum. As you can see here, the lowering of the thresholds of the preparation states that I spoke about, and the repression or decrease of frontal, let's say, repression on the preparation states again. Here we can see within the dream state, what happens is the activation of the mental simulations of these dream stages, one of which, again, eating ice cream. Underneath here, you see activation of the choices that weren't made. But it's important to show this because it shows that these choices were considered by us in our sleep, but the others were chosen as well, as you can see by the high activity. Most important here, these are the W states, which then you can see they continue being very active or remembered, even during wake, also when the second problem is reoccurring. And most importantly, we also modeled as an outcome the solution. Let's say there is a solution in our dream that we had before, which is over here. We will forget about it during the day because we don't necessarily think about our dream, but once the problem reoccurs, we will again think about our dream, and because the connections were so strong, we remember again, oh yes, this was the solution to my problem. Next part was without dream recall, and you can see it's already quite different. Most importantly are these W states, which show they weren't as active as we saw before. And even when the problem is being recalled again, we just don't remember it that well. the important to see is that during the dream, we did come to a conclusion. So we did have a creative dream, let's say, but because we don't remember it and don't recall it, we also don't come to the conclusion again, even if we're confronted again with that problem, because again, we do not remember it. And then next, conclusion discussion. We think this is one of the first models that tried to demystify this phenomenon, and specifically creative problem solving. We did show with our model how it could be possible that this phenomenon occurs. Of course, there could be improvements to this model, and there are some limitations. First of all, this study was based on theory. It would be nice if there was some more data, experimental data on it. As well as I said before, the dream sequence is just not very realistic. It's made for simplicity, because normally it would probably be a big expansion of choices that you can make in your dream, or how we can model that. Subsequently, there is possibly, most likely, other biological underpinnings of dreaming and creativity. And I specifically want to note that we use the BFC as an assumption, or as a ground region in this paper, but there's a high possibility, or it's possible that that's a more specific reason or region that is inherent to this phenomenon. And also approach-related traits, such as how open am I even to use this dream to solve my problem, for example. But overall, we think this is a good foundation to demystifying this phenomenon that may have led Kekulé to thinking about the benzene structure, as well as how we might think about solutions in our dreams. So that was our paper. Thank you for listening. Do you have a question? Oh, I do not hear.
Thank you for the presentation. We will now proceed with questions from the audience. If anyone has a question, please raise your hand. Okay.
I have a question.
Yes.
I have a question about it's quite promising modeling. About your last comments about regarding the improvements. I was thinking in this realistic. There is a series of experiments using imaging, neuroimaging during waking. The people waking. It's from California, the University of California, and they register in magnetic resonance the imaging that possibly has to do with the imaging they just saw, they were presented. And that kind of phenomena, I think that would be very interesting to fit your model. And the other stuff that I was thinking is when you said about this more realistic neuroscience data from neuromodulatory incomes, inputs, outputs would only add to the possibility. But I was thinking that not just the possible decisions, but the using of data from images, representation of images could be very interesting for your work.
Thank you. There's a way for you to send me some that would be also nice, and I can look it up definitely. Thank you for your comment.
Any other questions?
I also have a question.
Yes.
Do you think that with this model that you're used, it is possible to represent a dream where different things happen at the same time? Because it seems that you're always putting things in sequences, but I was wondering if you could represent something that are happening at the same time.
Yes, because our dreams are kind of in shambles usually. I think there could be a possibility. I wouldn't know how to answer it specifically right now, but there are modeling techniques for that to happen at the same time for multiple outputs to happen in, for example, one stage of dreaming. So I think my answer is yes, it is possible. But how? I could not answer right now.
Okay, thank you.
Well, it seems the time for questions is over. So if anyone in the audience have further questions, they can get in touch with the author directly. And we will now proceed with the next presentation, which is titled Existence, Hypotheses, and Categories in Knowledge Representation.
I'm Ricardo Woodley.
Okay.
Is this one? 9-1. Yes, that's this one.
Porque no te escuchas por los murió.
Can you put in full screen? I don't know. I think it's a visualization. Probably.
Okay, you have 15 minutes to present your work and 5 minutes for questions.
Okay.
We remind everyone in the audience to please mute your microphones while the presentation is ongoing. And Mr. Ricardo, you can begin.
Can you hear me? No. No. I think the other one. Hello? Hello? Okay. Okay, my name is Ricardo Gudin, and I'm going to present this work, Existence, Hypothesis, and Categories in Knowledge Representation. This is a work that is being developed together with Eduardo Camargo and Eduardo Yuji Sakabi, which Eduardo is a postdoc that is working with me, and Eduardo Sakabi is a master student. Well, the talk is about knowledge representation. And we know that knowledge representation is one of the most critical issues. Oops. Can you turn me back? Right? Yeah, please. Okay. So knowledge representation is one of the most critical issues while developing a cognitive architecture. Depending on the cognitive architecture that you are working with, you have different means for representing knowledge, and depending on the means that you are using, you are going to be able to represent parts of the reality that you cannot if you use a different mean of representation. For example, the SOAR cognitive architecture uses the working memory elements and rules, so we are in some sense tied to what can be represented by working memory elements and rules. The Clarion cognitive architecture uses a different approach. They use dimension value pairs, rules, and neural networks. ACTR uses chunks and rules. The LIDA cognitive architecture uses node networks and codelets. Other architectures can use things like propositions, predicates, atom spaces, beliefs, and any other kind of representation. And the problem is that when we are tied to a particular representation scheme, this limits us on the kinds of phenomena from environments that the architecture is able to cope with. So in this sense, the architecture might be blind for some facets or features from the environment which does not fit into this representation scheme, okay? So with that in mind, we are proposing here one way of representing reality or representing whatever we want to represent inside the cognitive architecture, that is what we call an idea. well, it's not exactly a new idea because the idea of idea is in everybody's mind. But the idea or the computational idea is the building block for knowledge representation in CST. CST is our cognitive system toolkit, is a toolkit being developed by our research group for creating cognitive architectures. This whole idea of idea can be both a theoretical and can be used in a theoretical and in a computational perspective. An idea can be used to represent single properties up to very complex concepts like structures, trees, graphs, or networks. So the beauty of this thing is that with this idea of a computational idea, I can represent virtually everything that I would like to represent. Okay. One interesting particularity of our proposition for a computational idea is that our ideas can refer to existence, and for existence, I am talking about the states of affairs that are really happening at the environment. So I'm talking about whatever is here around us, okay? But our computational ideas can also be referred to hypothetical or imaginary things that exist just in the realm of possibility. So they are not things that are supposed to be happening around us, okay? And this is a quite important feature because this is not so common to have things like that in other kinds of cognitive architectures. The computational ideas can also be used to represent concepts, classes, sets, or any other kinds of categories that could be important for us to talking about our environment or our real world. Okay. This notion of idea has background on cognitive semiotics and particularly on the semiotics of Sharp-Sanders Peirce. Well, this is a kind of a diagram that shows what we call the three worlds of ideas and the fragments of reality. So I will focus on each of these parts, so because it's difficult to see them in this whole diagram. But let's talk first about the world of existence. So what you're talking about here, we are talking about what can be represented by an idea. And in this case, we are talking about the world of existence, things that are in our real world, okay? And then we fragment that in three different kinds of levels of description of this existence. In the lowest level of description, we have what we call the world of properties. So this is, for example, what you can have with sensors. I can have a camera, and then I can have an image that will give us some properties of color, for example. I can have a sensor for sound, and then I will have the property of the sound over time. Okay. I can have other kinds of sensors, for example, sensors for temperature, sensors for pressure, or any other kinds of sensors. Then on the next level, we have the world of things. So we are not talking about just properties, but these properties are embedded into things, okay? And so we are not talking about anymore about, well, the temperature, or color, or sound, but we are talking about objects that are in the existence, okay? And so we have ideas that are being used to represent these objects. But objects are absolutely nothing if we don't consider time, because over time, these objects could vary their properties, okay? And then we'll need to have our ideas to represent episodes, okay? And what is an episode? An episode is something that I have a list of objects or a list of things that are moving around time, changing their properties around time, and then I will need to have a proper way of representing these episodes in time. Okay, and so you could see that with these three different words, we can have the three fragments of reality. And in this case, particular case, I am talking about the world of existence, things that really happened, and the architecture is referring to these things that really happened. Okay,
Then we have what we call the world of hypotheses or the world of possibilities. In this case, what we have, we're not talking about something that really happens, but I'm talking about hypothetical things. I am talking about a hypothetical temperature. I'll be talking about a hypothetical color, a hypothetical pressure, okay? And so I will have the same three words, the word of properties, the word of things, and the word of episodes, but now being considered in this hypothetical thing. This could be, for example, something that I am planning for the future, or maybe I'm just making hypotheses considering possibilities of actions, or I'm just remembering something that is vague and I don't really can precisely focus them on the existence. So it's a completely new world that would be represented by these ideas, okay? And finally, I have what I call the world of laws. So, or the world of categories, okay? So a category is represented by a law that includes something or not in this category, okay? And then again, I can have categories for properties, I can have categories for things, I can have categories for episodes. And so again, we are going to see the same sub-words of the fragments of reality happening in these words of laws or the words of categories, okay? Well, then how is the way that I can conceive these computational ideas inside a computer program, okay? And this is the interesting model that we have. This computational idea is basically a conjunction of something that I call a value, and a value can be a number or a symbol, okay? In this very small representation, I will show later how we can expand that to be more complex, okay? This idea must have a name, it must have a category name, and it must have a scope. And the scope is exactly based on this, if I'm talking about the world of hypothesis, the world of existence, or the world of categories or law, okay? And then the most important part of this model, do I have a pointer here to show? Not this thing. Yes, but oops. All right. I want to move to the conclusion so fast. Okay, no problem. I can. No problem. Just yeah. This is okay. Thank you. So, oops. We need to show it here.
No, you can.
Oh, you can show them. Okay. So this is the most important thing. This idea that refers to other ideas, because this is the key issue in this model. Because if I can refer other ideas to my idea, I can start creating complex ideas, and with that we can absolutely represent everything. Okay, and I will give you some examples for you to understand better, but these ideas can be of many different types. So I can use this to represent properties. I can use this to represent things. I can use this to represent time steps, episodes, quality dimensions, and affordances, okay? And I will jump to some examples, okay? We have created this idea editor, which is a way of visualizing these computational ideas in a more easily way, okay? So I have created these kinds of icons just to show the different possible things that could appear inside an idea, okay? For example, I can have a property that is in the world of existence. I can have a property that is in the world of hypothesis. I can have a property that is in the world of categories. Also, I can have episodes of the three types, things of the three types, okay? And based on that, we can create very interesting kinds of ideas. Okay, so take this example of an idea of an episode. Okay, I will go first with the most left idea. So I want to represent an episode, an oven heats. And in this case, I am talking about a real oven because I am representing it on the world of existence. So I am talking about an oven that I know, okay? And I know that in instant zero, this idea is represented by an oven, okay? That we have a token of an oven. You can see that this oven is green. This means that the oven is also in the world of existence. It's a real oven, an oven that I know, okay? And it has a temperature that is 25 degrees. And there was a precise time when this happened, because this is an episode that really happens. I'm talking about the existence, okay? And what happened is that in a second time, in a time one, okay, the same oven now has a temperature of 200 degrees, okay? And so I am representing what here? I am representing an episode that happened in the real world, okay? We are aware of that. There is a real oven that I know which oven is that, and I know the temperature that this oven had in the precise time, and I know the temperature that the same oven has in another time. So it's a complete description of this episode that this oven heats, okay? Now compare that to the second idea, which is more or less the same, but in a different, with some different qualities. First of all, in the second episode is a hypothetical episode. So I'm not talking now about a situation that really happened. I am talking about a hypothetical oven. So it's not just an oven that I know. It's not the oven in my house. It's not the oven in a restaurant. It's a hypothetical oven. Okay, so it's important because it's a difference between this oven and the oven on the first episode. Okay, in this time, the time is unspecified. So I don't know when this happened. Okay, it could be even it could be the first one, but I don't know. Okay, it's a hypothetical time. And then I know that in a second instant of time that is also unspecified. I'm not specifying when it happened, but I am specifying that the temperature is higher than the temperature in the first time step. Okay, and so I can understand this as an episode that is a little bit vague, that is telling us that a possible oven in a possible instance of time has heated. Okay, so we need to understand that there is a difference between the first representation and the second one. Because in the first representation, I was representing something that really existed. On the second, I am just considering a hypothetical situation where an oven has heated, okay? And then there is the third kind of episode, which is still a different one, because in this case, I am not talking about neither in a hypothetical sense and neither in an existential sense. I am talking about every possible situation where a possible oven, hypothetical oven, okay, not a precise oven, because you can see that the oven there is blue, and blue means that I'm talking about in a hypothetical sense, okay, where there is a temperature that I'm not being precise about that, but you can see that it's red, so it is a temperature in the world of categories. So I'm talking about all the temperatures that are cold. Well, you know what is cold is, so you can precisely define what is cold, okay? The time is an existential one, so I'm talking about a real time, but I'm not specifying it, okay? And then this same oven in the future, we will have a temperature that is hot, okay? So you can imagine how many different representations I can do with that, just changing these little things, okay? I can change existence to hypothesis and then to category. And then, well, this same story can be told in many different ways. So it's a quite interesting thing that we can do with this thing, okay? I have another example that is a little bit more complicated, but just for you to realize. So in this case, I am trying to represent a situation where John gives a gift to Mary, okay? And again, we can talk about this in the sense of existence, in the sense of existence, or in the sense of hypothesis. And then again here, oops, I'm having problems with the battery of the microphone. They are trying to find another one, but nevertheless, I will try explaining.
We can listen, but
yeah, but people in the people in the remote, they cannot. Well, I'm not going into the details. Yeah, this is artificial life. The technical problems are being solved. Just a little patient. Okay. The technical problem is almost solved. Okay. Thank you. And I'm not going to enter into the details, but you can later take a look on this example in the paper, and you can see that again, I will be playing with this thing of parts of the idea are from the world of existence, parts of the idea are from the world of categories, parts of the ideas are on the world of hypothesis. And with that, I can create very different situations of descriptions of episodes, okay? And I also hope you to see that in this case, what I have an idea that is an episode, and within this idea, I have another idea that is a time step. Within this time step, I can have an idea of thing. Within this idea of thing, I can have a property, and so we can use this property of a computational idea to refer to other ideas to create quite complex ideas, and with that, I can virtually represent everything I want, okay? Also here again, I have the same thing applying an episode on the world of categories, an episode on the world of existence, an episode on the world of hypothesis. And with that, we can have many different possibilities. I'm not going to take too much time, but you can see these examples later on the paper, okay? So to conclude, it's very important to have the consideration of scope, which is one of the main contributions of this presentation. So the scope can be in the world of hypothesis, the world of existence, or the world of categories. And this allows for many different kinds of knowledge to be represented. You can see that all these representations are similar, but indeed they are different ideas and they are able to be represented by our version of computational ideas, okay? Remembering that these computational ideas are the basic knowledge representation scheme that is used in the cognitive system toolkit, which is the toolkits that we are developing in our research group. To represent them, we have these issues of name, value, category name, scope, and list of related ideas. This is a flexible and powerful means for conveying different facets of reality, and it is tailored to fit since simple numeric or string type ideas up to very complex data structures using a unique knowledge representation scheme. So the beauty of this is that just with a sense knowledge representation scheme, I can represent very different kinds of facets of reality, okay?
Up to our knowledge, CST is the only cognitive system addressing this issue of distinguishing among hypothetical episodes, things and properties versus episodes, things and properties that really occur in existence, and also the difference between instance ideas, those that are in the hypothetical and existence versus categories ideas, which is also an interesting contribution. As you can guess, this is a work in progress that brings many insightful considerations. And that's it. Thank you very much.
Thank you for your presentation. Now we will proceed with questions from the audience. If anyone has any questions, please raise your hand.
You want to come here? Just to choose the microphone so people can. Thank you.
Good afternoon. I have just a question. How do you represent the change between ideas? I mean, you say a lapse of time change the features, but that can change the idea too. And how do you represent that into your system?
The point is, when we are thinking about a change in ideas, this change always materialize in time. There is no way in which we can think about a change that don't happen in time. So the only thing is that I just put two different time steps, one time step, another time step, and then I can change whatever is in following this on the tree. This could happen in a different way on the second tree, and then I will have a difference in idea. This could be, for example, a change in category. Okay, in the first step, my notion of cold temperature is 1, and then in the second time step, I enlarge this a little bit. So what was colder in the past, now it's a little bit different. I am considering a higher subset of temperatures for being cold. Okay, so I can also represent the change of ideas using this same kind of representation. Okay, thank you for your question. More questions?
No? Okay, I have a question. When you talk about the time, I am a little bit worried about how much memory do you need to represent that causality. Okay, because you have an object in one time and you have another the same object in different time. The object change, the scene change, the context change. Now, how you in your implementation consider that?
Thank you for your question. I will rely on this example here. Okay. I didn't have the chance to enter into too much details, but you can see this. There is one of the properties of the time step that is transition. In this particular case, I am putting transition linear, which means that I am just picking samples on the evolution of time. Okay, and then I am moving from the temperature of 25 to the temperature of 200 in a linear way. Okay, it could not be linear. It could be, for example, an exponential, or you can just define any kind of profile. But the point is, I need to represent only the significant time steps. I don't need to represent all the time steps. Of course, that if you are talking about something that has a large development over time, this can consume a lot of memory. But using this and using this property of defining how is the transition, I can use some kind of regularity on the passage of time that I know that is for sure, and I can use that to minimize the quantity of memory that I need to represent in this case. Okay.
Okay. However, the problem exists.
Yeah, of course.
Yeah. and this means that our brain ought to solve that problem in a way. I don't know the way.
Well, I believe that the way is to find some kind of regularity, because once that I discover a kind of regularity on how this transition happens over time, I can use this regularity and create some other part of other idea that represents exactly how this evolves.
Yeah.
Okay? And I can insert that into the model.
But is that translated problem to another problem, because we need to find or imagine or know a function that can model the transition.
Yeah, if we go, for example, in the control system in electrical engineering, we have exactly the same problem. And what people do is to appeal to linearization. Okay.
Yeah.
And so always we can use linearization to compact this transition. It's not going to be a completely precise description on how time evolves, but in most of the cases, linearization can be a very successful use for having this compression of knowledge into smaller pieces, and so we can find a representation.
Yeah. Okay, thank you very much.
Thank you. More questions?
If there are more questions? No more questions? Yes? No?
So thank you very much.
Thank you very much. And I think, thank you.
Okay, we will now proceed with the next presentation titled Adaptive Network Modeling on the Influence of Leadership and Communication of Learning within an Organization, that will be presented by David Bowman.
Hi.
I think that you need to.
Okay, are you ready to share your screen?
Yes, you should be able to see it now. Is that correct?
Yes, perfect. You have 15 minutes to present, and then there will be 5 minutes for questions from the audience.
All right, perfect. Thank you. So hi, I am Debbie. This presentation will address the influence of leadership and communication on learning within an organization by direct mutual interactions in the dyads. This is done in combination with multi-level organization as an alternative route, which includes feed-forward and feedback learning. First, I will start by explaining the multi-level organization learning. The concept of multi-level organizational learning is not new, but the combination with artificial intelligence is still quite new. Organizational learning is a shared knowledge development process involving individuals, groups, and the organization. It occurs firstly through the exchange and formation of shared mental models between team or project members, and secondly, through the institutionalization of these shared mental models on the organizational level for future use. This process is referred to as feed-forward learning. And learning also occurs in the feedback direction when the institutionalized learning and the shared mental models are being transferred and used by teams and individuals. Using computer simulations, we can determine the quickest and most efficient way to share knowledge. And in this research, we will look at 4 different models based on an active and inactive team leader, as well as high or low extent of natural communication. I will start by explaining a little bit of background knowledge. The first step is about mental models, but specifically shared mental models. A mental model represents events and processes from the world and include information we know as well as our beliefs. Through a person's mental manipulation or internal simulation, mental models are capable of understanding and explaining phenomena and thus react appropriately. Mental models rely on 3 assumptions. First being that each mental model represents a possibility. The second is the principle of truth, meaning that the mental model represents what is true according to the premises, but by default not what is false. And lastly, that the deductive reasoning depends on mental models. When working in teams, every person has an individual mental model, but will form a shared mental model. These shared mental models combined with beliefs are important in organizational learning. Next, I will explain a little bit about organizational learning. Humans have the ability to act in groups and through joint actions, and in such joint action, the group creates a set of intersubjective meanings that are expressed in their communication, either verbal or non-verbal, or through acts or even objects. Communication includes metaphor, myths, etc. These are shared within the group. New members will initially have little to no idea of the communication within that group, but with time they learn. Organizational learning looks at how people will learn from other people and their experience. In parallel, individuals simultaneously adapt their behavior based on organizational routines and processes. There are three observations that form organizational learning. The first being that organizational behavior is based on routines. Secondly, actions made by organizations are often history dependent. And lastly, organizations are oriented to targets. Organizational learning is considered a multi-level phenomenon that involves individuals, teams, and organizations, and the connection between those. This learning process works in feed-forward and feedback directions. Feed-forward learning means that the organizations can learn from individuals and teams, and feedback learning refers to the utilization of already existing and institutionalized knowledge, and sharing this with individuals and teams. Features of individual memories have an influence on the organizational learning, and the formation of a shared mental model is usually part of feed-forward organizational learning. The last piece of background information is leadership. There's an established link between leadership and organizational learning. In a study conducted in 1939 by psychologist Kurt Lewin, there were 3 different styles of leadership identified. I will explain them very shortly. The first being authoritarian. Here, the leadership provides clear instruction of what is needed and expected. The second being participative. Here, the leadership involves a leader who's very involved with the group and involves other members in the decision making, as well as providing guidance when needed. The last leadership identified by Lewin was delegative, and this focuses on delegating initiative to team members. However, recently there were some more leadership styles that have been added, first of which being transformational. In these groups, leaders inspire their followers, and transactional. This is often seen in work environments with an employer and an employee. The employee has the role of a follower in exchange for compensation, often money. So this was all the background information, and now I will describe a real-world scenario on which this paper is based. It is based on a case described by Amy C. Edmondson, which looks at the role of learning within teams, and this is done by observing several teams, and the collective learning process is investigated by looking at the team's reflection and action. In Edmondson's paper, an organization with 12 different teams organized in 5 different team types, and these teams were divided into 3 different groups. 1, reflection and action. 2, reflection without action. And 3, neither reflection nor action. We picked a team called Product Development Team because they had teams in both Group 1, which was reflection and action, and Team 2, which was reflection without actions. These teams were discussed in depth in Edmondson's paper, and therefore we felt like these would be the most realistic when simulated because we could provide a lot of information without having to assume a lot of things. In this way, the following situation was created. There is a team whose job it is to promote a new product. The relevant team members in the situation are the team leader, which is shortened to TL, the marketing consultant, shortened to M, the designer, shortened to D, and the final representative, shortened to F. The marketing consultant suggests billboard as a way to advertise a new product, while the designer suggests social media. For both ideas, there's money needed from the financial representative. So the team leader suggests that both team members talk to the financial representative. So I hope it's visible clearly. This is the formula for canonical differences, and there are several characteristics in a network model namely connectivity characteristics. These refer to connections and their weights between states, and they can be seen in this formula. And aggregation characteristics, which calculate the impact from incoming connections, and timing characteristics, which is a speed factor. These two formulas are the functions used in the self-modeling network. Realistic networks models are usually adaptive. This is because both their states and network characteristics change over time. By using a self-modeling or reified network, a similar network model conceptualization can be applied to adaptive networks to obtain a declarative description using mathematically defined functions and relations for them as well. The introduced second-order adaptive network model addresses the effect of communication and leaderships on learning within an organization. Communication can occur by either natural communication or communication organized by the team leader. In this paper, natural communication is described as communication that happens naturally without extra encouragement from the team leader within the team. Before we started simulating, we made several assumptions, first of which being that the natural communication is either completely off, so low, or completely on, so high. This natural communication can be adjusted for every diet. The second assumption we made is that the level of encouragement from the team leader is also a spectrum. Communication within team members in diets, as well as the relations between team members, can be adjusted by the team leader. Third assumption we made is that there's also a spectrum from feedback and feed-forward learning. Next, we made the assumption that if the team leader states that something will happen, it will happen. This means that nobody overrules the team leader. And last, we assumed that the simulation by the model follows 3 phases, and these phases do not overlap. The first phase is the natural communication and the team leader interactions. Here, employees are learning by mutual interaction in diets. The second phase is feed-forward learning, and here a shared mental model is formed. And in the last phase, feedback learning is presented. The connectivity can be seen in the following graph. I won't bother you too much with the details because it's, as you can see, it's very overwhelming. So I'll skip to the results. Oh, sorry, scenarios first. We made 4 different scenarios. The first being the base scenario. Here there was neither an active team leader nor a high level of communication. Our second scenario was an inactive team leader, but a high level of communication. The third being an active team leader, but a low level of natural communication. And the fourth and last scenario was both an active team leader and a high level of natural communication. Here the simulation results of scenario 1 can be seen. As you can see, 20 to 60 is the first phase, and you can see that there's no communication here. Thus, there's also no learning. The learning only starts in phase 2, which is 60 to 120. As you can see, this learning is only feed-forward organizational learning. Thus, the organization is learning, but the team members are not yet. And the team members only start learning in the learning feedback phase, which is phase 3, which is 140 until 180. These are the simulation results of scenario 2, which had an inactive team leader, but a high natural communication. And because of this, the team members are already learning during phase 1. And in addition, organizational learning happens in phase 2, similar to scenario 1. However, since the team leader and since the team members have a good communication, the knowledge is already shared. These are the results for simulation for scenario 3. But similar to scenario 2, the team members are already learning in the first phase. This is because the team leader makes sure there's communication within the team. Because of this, the team members are already learning in phase 1. And in addition to the information learning by the organization through feed-forward learning in phase 2 as well. This is the last scenario, scenario 4. Comparable to the previous two scenarios, in this scenario, the learning too is happening in phase one. In this case, the communication can happen naturally or through the team leader. This ensures that there's enough communication between the team members to establish a learning process in phase one. In phase two, this knowledge is shared with the organization during the feed-forward learning. And finally, in phase three, the feedback learning is updating the individual mental model as needed. So the results show that when good communication is present, either due to the team leader or due to network communication or both, this can lead to faster learning processes within an organization than the longer route via feed-forward and feedback learning. However, this more direct form of learning in general may take more of the employee's time, as a quadratic number of dyadic interactions in general requires more invested time than a linear number of interactions needed for feed-forward and feedback learning. Learning between team members takes place when there's at least one basis for communication. In the three latter scenarios, the graph was quite similar. They only differ in ways that cannot be seen in these graphs. When there's only an active team leader, this person is often seen as the boss and treated as such. And this team leader is very important because they make sure that everything that needs to get done will be done. However, this can lead to the hierarchical mom effect, which is defined as individuals' reluctance to provide negative feedback to another for fear of being associated with the message. This means that people are less likely to say something to their supervisor, even if it's at the expense of task accomplishments, because they want to maintain a positive relationship. This can be seen specifically in work relationships. Another factor is that team members are more likely to expect negative feedback from their team leader than the team leader expects negative feedback from them. This may negatively influence other people, team members, to expressing their negative opinion. Other research has shown that when there is a two-way symmetrical communication system, which also includes internal team peer communication, the likelihood of an employee's job satisfaction increases, as well as their participation and commitment. Internal communication helps team leader connect with their members and thus help the organization with bettering its environment. So the presence of an active team leader as well as network communication leads to a more satisfactory work experience. When there's only a high level of network communication, team members may learn a lot from each other, but things could still be missing. Like mentioned before, a team leader is important because they ensure that everything that needs to be done will be done. When this responsible person is missing, it could be that some things are missed or stay undecided. Thus, even though the three latter scenarios had to an extent the same outcome, there still could be differences that are not shown in the graph. The result of this being a computational model leads to the fact that it does not fully cover reality. There might be other factors important in an organization that might influence the learning processes. Examples of this are the amount of people in an organization, the relationship for each individual diet, the type of project they're working on, the list goes on and on. It's not suitable to create a real-life experiment of this. This is because some scenarios, like an inactive team leader and low network communication, could lead to hostile work environments. And for further research, differentiation within a scenario could be made. For example, two communications have a high level of natural communication between them, but not with another coworker. However, for the sake of simplicity, this was not addressed yet. Further research could also look at larger teams or more layers within the team. This was everything that I said in my paper. Are there any questions?
Thank you for your presentation. I will now proceed with questions from the audience. If anyone has a question, please raise your hand. I have a question.
Hi. I was wondering if your model can give us, for example, for management science, an idea of what is the best kind of leadership in terms of efficiency. For example, if you could
model different kinds of leadership and see the productivity that can happen depending on the leadership that you impose. Do you think that your modeling could provide this kind of hint for management science?
Thank you for the question. This is actually something we did think about a little. As can be seen in the scenarios, I did mention some leadership styles here. For example, the inactive team leader and a high natural communication could be because the team leader is very delegative and trusts their team to make the right decisions without them. So it could be that the team leader just at the start of the project says, "Hi everyone, good luck, goodbye," and leaves it to them without taking too much of an authoritarian leadership role. Which can be seen in an active team leader, but in low natural communication. This is, in my opinion, usually a transactional or authoritarian leadership, because every team member can just get their task and just do it without having the need to communicate with other team members. This could be, for example, in the scenario where there's a new team with an already experienced team leader. And in scenario 4, where there's both an active team leader and a high natural communication, I thought that was most likely linked with participative or transformational leadership, because in those two types of leaderships, the leader is actually really enthusiastic and involved in the project, which I think could naturally lead to a higher natural communication. And this could be, for example, when team members and team leaders are familiar with each other already and feel more comfortable. And in scenario 1, when there's neither an active team leader nor high natural communication, I don't think that fits any leadership, but we had to put it in as a baseline.
But do you think it's possible, for example, this kind of leadership is 35% better than the other one, or numerically giving the influence of leadership in the final productivity that the team will exhibit?
Yeah, that could be. But in order to do that, I think our simulation has to be way more detailed, and we didn't unfortunately have the time for that. So it's very simplified, why I think there is not a lot of differences that can be seen in the graphs. But I think it's definitely possible if the models are less simplified.
Okay, thank you.
Thank you for your question.
Any other questions? There seems to be no more questions, so this concludes the presentation of this block and day. Thanks to all the presenters and to all members of all presenters for the audience. Activities will resume tomorrow according to the schedule. Thank you very much to everyone.
Comentarios para mañana, el segundo no va a estar disponible.